Hello and welcome everyone. We're happy that we're all together again. In this tutorial, we will start talking about a new important topic in the field of the low voltage distribution system, which is the cables used in the electrical design. So fasten your belt and let's get started. The aim of this tutorial is to know what are the electrical cables and what are the different types of cables used in the distribution system. So we need to recognize the different types of the cables which are used in the low voltage system to know how can we select from them while making our design. So let's go ahead. First of all, if we need to define the electrical cable, we say that it's a group of wires or a group of conductors that are grouped together and they are insulated by the same insulator. Like that cable here, you can see it consists of a group of wires that are accumulated together to produce the conductor, and they are insulated by this insulator. Also, this is another cable that has two different group of wires that are accumulated together to produce two different group of conductors, and finally they are insulated by the same insulator. And the same idea is applied to this cable, as it consists of some conductors and they are insulated also by the same insulator. Alright, now we need to know what are the different types of cables. Here we say that we can specify the types of cables according to some different paces, and the first pace we specify the cables according to is the type of core of this cable, and for this type of core we have two main types. The first one is the solid core cable, like that cable here. You can see its conductor consists of only one solid core or only one wire, not a number of accumulated wires. But on the other hand, the second type we have is the stranded cable, and this is the shape of the stranded cable. You can see its core consists of a number of wires, not just one wire or not just one solid core. And it's called a stranded cable as it consists of some stranded wires which are accumulated on the core of the cable. But now you can ask, what is the difference between the stranded cable and the solid core cable? Or why we need to use the solid core cable in some applications, and on the other hand or in some other applications we use the stranded cable. Here we say that the difference between the solid core cable and the stranded cable is that the solid core cable is less in price or it costs less, and this is because it has less conductivity, hence the resistance of the solid core cable is higher, and this means it conducts less electricity. On the other hand, the stranded cable costs much higher than the solid core cable, and this is because it has higher conductivity, so it conducts much current with respect to the solid core cable. So for the same cross-sectional area, we find the solid core cable to conduct less electricity with respect to the stranded cable. And by the same way, the stranded cable is much flexible than the solid core cable, as the stranded cable consists of some wires, so this accumulation of the number of wires in the same conductor makes it to be a more flexible cable or makes it to be more flexible than the solid core cable. Very good. Now the question is that, what does make the stranded cable to conduct much electricity with respect to the solid core cable, or what does make the stranded cable to be more better than the solid core cable? Here we say that for the solid core cable it consists of one core only, and there is an effect that appears when the AC current passes through the conductor, which is called the skin effect. And the skin effect means that a larger amount of current will pass through the surface of the conductor, while a smaller amount of current passes through the inner side of the conductor or through the core of the conductor. And the reason of having a smaller current at the core or at the center of the conductor is that there is a larger resistance of the core of the conductor due to an opposite current which appears on the core of the conductor. And this opposite current is called the eddy current, and it appears when the AC current passes through the conductor. And this eddy current works to opposite the original current and decrease it by increasing the resistance of the conductor. And as a result of the skin effect, we find the current of the core of the conductor to be smaller than the current of the surface of the conductor, or we find that we have a larger current at the surface of the conductor and we have a smaller current at the core of the conductor or at the center of the conductor. And for that reason, we use the stranded cable, which consists of a larger number of wires, and by that way we make the AC current to pass through all the surfaces of all of the conductors, and by that way we increase the area at which the current is moving through. Hence, we increase the conductivity of the conductor by increasing the area which the current is passing through. As we have much number of conductors, so the current will pass through the surface of all of them. Hence, we increase the area or we increase the surface of the conductor that the current is moving through. Very good. Also, we can categorize the different types of cables according to another pace, which is the type of material of the conductor itself, as the cable conductor can be made of aluminum or it can be made of copper. So the aluminum and copper are the most common materials that we manufacture the cable of. And for the copper cable, they have higher conductivity than the aluminum cables, so the copper has higher conductivity while the aluminum has less conductivity. And this is because the resistance of any conductor equals the resistivity of the material of this conductor times the length of this conductor over the cross-sectional area of this cable or this conductor. And because the copper has a lower resistivity, so it has a lower resistance. And due to the lower resistance of the cable, we find it to have a higher conductivity. While, on the other hand, as the aluminum material has higher resistivity, so it will have a higher resistance as the resistivity is directly proportional to the resistance of the cable. And as a result of the higher resistance of the aluminum cable, it will have a lower conductivity. So it conducts less electricity with respect to the copper for the same cross-sectional area. And also because the electrical losses of the power equals the current squared times the resistance, so we find the copper cable to have less losses than the aluminum cable. As the losses is directly proportional to the resistance, so when the resistance increases, the losses will increase, and when the resistance decreases, the losses will decrease also. And here the losses are smaller for the copper cable due to the smaller resistance of the cable, while the power losses is larger for the aluminum cable as the aluminum has a larger resistance. So this is a more benefit for the copper cable as it has less losses and less resistance, while for the aluminum it has a larger losses and larger resistance. Alright. Also, the next property we have is the voltage drop through the cable, which is the losses and the voltage through the cable itself. And we find the copper cable to have a smaller voltage drop than the aluminum cables, as the voltage drop equals the current times the resistance. Here the current is the current passes through the cable, and the resistance is the resistance of the cable itself. But the resistance of the copper cable is smaller, hence the voltage drop of the copper cable will be smaller as the voltage drop is directly proportional to the resistance. When the resistance decreases, the voltage drop will decrease. But on the other hand, we find the aluminum cable to have a higher resistance, so the voltage drop through the aluminum cable will be larger. And finally, we find the copper cable to have a higher price due to its good electrical properties, while the aluminum cable is having less price due to its less electrical properties. So if we buy a copper cable, it will cost much, but it will give us a higher electrical properties. On the other hand, if we buy an aluminum cable, it will be lower in price, but it will give us a lower electrical properties. More than great. So that's about this tutorial at which we started talking about the different types of cables, and on the next tutorial we will continue this topic Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. I'm very happy that we're all together again. In this tutorial we will continue talking about our new topic, which is the electrical cables. So fasten your belt and let's get it started. The aim of this tutorial is to continue discussing the different types of the electrical cables, as we need to cover this important topic to characterize any type of cables which we can face during our electrical design. Also, we will learn about the construction of the electrical cables to know what are the different components of the power cables, or what are the different components that the power cables consists of. So let's go ahead. If you remember, in the previous tutorial we categorized the cables based on the type of the conductor itself, is it a stranded conductor or a solid core one. And also according to the type of the conductor itself, is it an aluminum conductor or a copper conductor. And now the next phase we can categorize the cables according to is the number of phases that the cable consists of. Is it a three-phase cable or a single-phase cable? As for the single-phase cable, we have two types of cables which we can use based on the number of cores of this cable. And the first type of the single-phase cable is the two-core cable. And at that type we have two cores inside the cable itself. One core is used for the line conductor and the other core is used as a neutral conductor. Like that case here, you can see this is a single-phase two-core cable, as it has two cores, one for the line and one for the neutral. Also that cable, it has two cores, one for the line conductor and one for the neutral conductor. And we use the single-phase cable in case of having a single-phase electrical load that we need to supply with electricity. So the single-phase cable is used for single-phase electrical loads. Also, the second type of the single-phase cables is the three-core cable, and in that case the three cores are used, one for the line, the other one for the neutral, and the third one for the earth. As we are considering the earthing cable to be one core that is included in the same cable. And also, like that case, you can see we have three cores, one for the line, the other one for the neutral, and the third one for the earth. So this third wire will be connected to the external body of the load to absorb any leakage or to work as an earthing wire. So that's for the single-phase cable, which can be a two-core cable or a three-core cable. Now the second type is the three-phase cable, and the three-phase cable is used to feed a three-phase electrical load, and it has two different types. The first one is the four-core cable, and in that case we have four cores inside it, or four cores inside the same cable, which are the three phases, the phase R, the phase S, the phase T, and the fourth core is the neutral core. So we connect the three cores with the three phases, and we connect the fourth core with the neutral terminal in the electrical load. Also, the second type we have in the three-phase cable is the five-core cables. And in that case, we have five cores included in the same cable. The three cores, or the first three cores, are the three phases, the phase R, the phase S, the phase T, and the fourth core is for the neutral, so it's connected to the neutral terminal. And finally, the earthing core, which will be connected to the exposed parts of the electrical load, so it's connected to the external body of the electrical load to absorb any leakage in the current. So that's for the three-phase cable to be connected to the three-phase load, which can be a four-core cable or a five-core cable. Alright, but there is an important note here. In the actual design for the three-phase load, we use a four-core cable for supplying the load, which has the four cores, the phase R, the phase S, and the phase T, and the neutral core. While for the earthing core, we use a separate cable that is connected to the device external body. So we are not using a 5-core cable in the actual design, as the earthing core will be in a separate cable that is separate from the main cable, which has the 4 cores, the 3 phases, and the neutral. So we are using two cables, one for the earthing and the other one has 4 cores for the 3 phases and the neutral. Alright. Now we need to know what is the usage of the electrical cable in the low voltage system. So we need to know in which applications we need to use the electrical cable. Here we use the low voltage cable to be connected between the different distribution panels in the electrical system. For example, in this diagram, if this is a distribution panel and it will feed another distribution panel through one of its outgoing circuit breakers, we find that this sample is for the electrical cable which is used to be connected between the different distribution panels. So the cable is used to connect between the main distribution panel and the sub-main distribution panel, for example. Like that cable here, it's outgoing of the main circuit breaker and it's going directly to feed another panel, for example. Also, the second usage of the electrical cable is to connect between the distribution panel and the electrical load directly. For example, we have this distribution panel and we have this electrical motor. So we use a cable also to connect between them. Hence, the cable terminals will be connected to the terminals of the motor. Very good. Now we need to analyze the construction of the low voltage electrical cables. So we need to know what are the materials that the low voltage cables consists of, or what are the different components that the electrical cable consists of. Here we find that the first layer that the cable consists of is the conductor of the cable itself. So the conductor is the most inner part or the most inner layer that the cable consists of, and it helps in conducting the electrical current. And this conductor can be a copper conductor or an aluminum conductor. Then the second layer we have in the cable is the insulation of the conductor itself, and this insulation is the second layer of the cable, so it's the second inner layer of the cable. And it's used as an insulation for each phase conductor to insulate each phase from the other phases or from the other conductors. So each core of the cable will have an insulating layer. And this insulation can be made of a material which can be a PVC or an XLPE material. So the PVC is the abbreviation of polyvinyl chloride, and the second one, which is the XLPE, is the abbreviation of cross-linked polyethylene. But we need to know now what is the difference between the PVC and the XLPE insulator. Here we say that for the PVC or the polyvinyl chloride, which has this shape, it has some special properties, which is that it's a flexible material, so it's more flexible than the XLPE insulator. And also its second property is that it can withstand a less temperature, so it withstands a temperature up to 70 Celsius. And this means if the cable temperature increases due to an increasing current that is passing through the cable, this PVC material at that case will withstand a larger temperature up to 70 Celsius. And also the next property of the PVC insulator is that it has a larger thickness. So the thickness of the PVC insulator is larger than the thickness of the XLP insulator. This is for the same cross-sectional area of the cable or for the same rating current of the cable. But the advantage of the PVC insulator is that it has a less price than the XLPE insulator. And for that purpose, it's the most common type of insulators. So in most of applications, we use the PVC insulator as it's used in most of the distribution applications. On the other hand, the second type we have, or the second type of insulation we have, is the XLPE, or the cross-linked polyethylene, and its properties is that it's less flexible, so it's less flexible than the PVC insulator, as it's hard in its bending operation, and also it withstands a larger temperature than the PVC insulator, so it withstands a higher temperature that is up to 90 degrees Celsius. So if the cable temperature increases due to the increasing of the rated current through the conductor cable, Here, the XLPE material will withstand a larger temperature up to 90 degrees Celsius. And also the XLPE insulator has a smaller thickness, so its thickness is smaller than the PVC insulator. And for all of those purposes, we find the XLPE insulator to be more expensive than the PVC insulator. Hence, the XLPE insulator is less popular than the PVC insulator. So we use the XLPE in some specific applications, while the PVC is used in much popular applications and the different distribution cases. And because the XLPE insulator withstand a larger current, so it's used in the applications where a larger current passes through the cable, which may produce a larger heat. For example, we use the main distribution panel cable to be an XLPE cable, as the main distribution panel carries a larger current, so the XLPE cable will withstand this larger current. More than great. So that's about the second component used in constructing the electrical cable. And on the next tutorial, we will continue illustrating the rest of the low voltage cables component. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we are all together again. In this tutorial, we will continue talking about our topic, which is the electrical cables. So fasten your belt and let's get started. The aim of this tutorial is to continue learning about the different construction components of the low voltage cables. So we need to know what are the different layers that the cable consists of. So let's go ahead. Now the third layer we have which the cable consists of is the filler material or the padding material. And this filler material is the material that lays here, which uses to fill the spaces between the different cores of the cable. As there will be some spaces between the different cores, so to have a strong mechanical structure of the cable, we need to fill those spaces between the different phases. And for that reason, we use this filler material that is called the filler or the padding. So it's used to fill the spaces between the different cores. Also, this filler material has another job, which is to protect the cable from the salts that lays on the ground or on the soil. This is in case of the cable lays on the ground, as when the cable lays underground, there will be some salts on the soil, so those salts harms the cable badly, as they may produce a corrosion of the cable material. Hence, we use this filler material to against the salts of the cable, not to result on the cable corrosion. Alright, now the fourth material we have is the inner sheath, and the inner sheath is a PVC material that is used as a coating for all of the three phases, so it's used to collect all of the cores of the cable at one unit. And also it may be used to make a uniform electric field of the cable, as there is an electrical field due to the passing current of the cable. Very good. After this inner sheath, we have the fifth layer, which is the armoring of the cable. And this armoring of the cable is a layer that is used to reinforce the cable or protect it from any mechanical stress. So it's a layer that is made of steel and is used to protect the cable from any stresses that may be applied to the cable. And this armoring layer has two types. The first one is called the steel wire armoring. Like that case here, you can see it consists of a number of steel wires that are used as a protection layer for the cable to protect it from any shock. Also, it reinforces the mechanical structure of the cable, and it's used to protect the cable, as we said, from any mechanical stresses. But the important note here is that this layer of armoring can be used or not. So for the same type of cables with the same cross-sectional area, we find the cable to have an armoring layer, and we can find some other cables with some other properties but without the armoring layer. And this depends on the application at which they use the cable. As if we are using the cable to be installed underground, we will use this armoring layer. Like that case here, you can see the cables are installed underground, so it's needed to have an armoring layer as the cable may be exposed to the mechanical stresses. While if the cable is installed on a cable tray, for example, so it's not needed to be armored, as there may be no mechanical stresses that is applied to the cable. Very good. Also, this steel wire armoring has more advantages as it's more strong, so it represents a strong protective layer, and for that reason its price is high. So if we put a cable with a steel wire armoring, it will cost much. Very good. Now the second type of armoring we have is the steel tap armoring, and in that case we use a steel material also, but it's a thin sheath or a thin steel sheath that is rolled around the cable like that case. And it has the same properties of the steel wire armoring, and it's also used if we are using the cables underground. But the difference here is that, or the difference between the steel wire armoring and the steel tap armoring is that here the steel tap armoring is less strong than the steel wire armoring, and for that reason it costs less. So the mechanical strength of the steel tap armoring is less than the mechanical strength of the steel wire armoring. And also we buy it with a less price. Good job. Now the final layer we have of the cable construction is the outer sheath, and this outer sheath is the final layer that is used to collect all of the inside layers inside it to protect the cable as a final layer. And also it's used as a protection layer, so it protects the layer from any outside mechanical stresses. And this layer is always made of PVC, so it's a PVC layer that is used as a final layer to work as the final package of the cable. So it protects the cable as a final layer from any outside mechanical stresses. More than great. So that's about this tutorial at which we learned about the all components that are used in the low voltage cables. Hope that's the key right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In this tutorial, we will continue talking about our topic, which is the electrical cables. So fasten your belt and let's get started. The aim of this tutorial is to know how the cables are installed, or what are the methods of installing the low voltage cables by knowing the different steps of installing the cables. So let's go ahead. Now the first method of installing the electrical cables is the electrical conduit. So in that method, the cables are installed inside some electrical conduits, which may be made of PVC material or it may be made of a metallic conduit. And this method is the method which we illustrated before for installing the lighting cables and also the switches cables that may be installed on the ceiling like that case here. So this is the first method of installing the cables at which we install the cables inside the conduit, and we use this method in case of single core cables or in case of a number of cables that are separated from each other, and this is also in case of the cables are having a small cross-sectional area. So when having smaller cross-sectional area or when having some single core cables, at that case we use this method, which is to install the cables inside the conduits. Very good. Now the second method of installing the cables is the free air, and at that case the cables are installed directly in the free air, so the cables are carried in some means of the cable trays. And the cable tray is a long steel box that the cable is moving through, which looks like that case as you see. This is a cable tray, which is a steel box, but it's open from the top as you see. And those cable trays are installed in some places where there is no ceiling to install the cables at them. So we use the cable tray as a method for installing the cables in case of there is no closed ceiling to add the cables at which. And those places at which we install the cable trays are places like the factories or the tunnels. As you can see here, those are some cable trays that are installed on the factories, and also you can see here the cable trays are installed in the tunnel. So the cables are installed on the free air as you see. Alright, now we need to know what are the dimensions of the cable trays, or which are the available dimensions of the cable trays that we can find in the market. Here we find that for the width of the cable tray, it ranges from 5 till 100 centimeter. So the smallest width of the cable tray is 5 centimeter, and the largest width of the cable tray is 100 centimeter. Also, for the height of the cable tray, we have 3 standard heights, which are 5 centimeters, 8 centimeters, and finally 10 centimeters. So those are the 3 standard heights we can find for the cable trays. Here 5, 8, and 10 centimeters. For example, if we need to install 3 multi-core cables on a cable tray, and each cable of those multi-core cables has a total cross-sectional area of 10 centimeter, so at that case the total width of the 3 cables will be 3 centimeters, and here it will be suitable to use a cable tray that has a total width of 50 centimeter, as at that case we will have the required offset distance between each cable and the other. And also we can install some single core cables or a multi-core cable on the cable tray, not only the multi-core cables. So anyway, all the options are available to install single core cables or a multi-core cable. And also we can say that the cable tray is the best method of ventilation for decreasing the heat of the cables. This is because the cables at that case are exposed to the free air, as the cable tray is open from the top side, so it's a good method for ventilating the cables or decreasing its temperature. While if the cables are installed underground, for example, or inside the ceiling, its temperature will increase as it's installed on a closed area, not an open area. So for that reason, this is a benefit of the cable tray, which is to ventilate the cable as it's installed on the free air. Also, we have another method for carrying the cables, which is similar to the cable tray, but it's used for some other types of cables. And this method is called the cable trunk. And the cable trunk differs from the cable tray in that the cable trunk has a cover from the top, and this is to close the trunk. Like that one, as you see here, it's a closed box, so it's not open from the top, or it's a closed box from the top. And this type is used for carrying the communication cables and the light current cables or the light current signals. While the cable tray like that one is used to carry the power cables. So for the cable tray we carry the power cables, and for the cable trunk we carry the communication cables. Very good. Now the third method of installing the cables is to install the cables underground. And at that case, the cables are installed in the soil, like that case here, and at that case, the cables are needed to be armored. As we said before, this is to avoid the mechanical stresses or to avoid the forces that may be applied to the cables when it's used underground. So we use the cables which are steel wire armored or steel tap armored for underground installation. But in case of the cables are not armored and we need to install them underground, we install them inside some tubes. So the tubes at that case will work as a protective cover for the cables. And at that case, the hole that is dug for the cables to be installed inside is called a trench. So the trench is a hole that is dug inside the ground for the cables to lay on. Very good. But we need to know now what are the properties of this trench, or what are the parameters of this trench that we design the trench according to. Here we say that the standard depth of this trench is 80 cm, so we dig a hole with a depth of 80 cm to install the cables at which. This is for the trench depth. And for the trench width, we made its width to be 40 cm. This is in case of having only a cable that is installed inside the ground. But in case of adding more cables, we increase the trench width by 20 cm for each added cable to the trench. Which means if we need to install 2 cables, the trench width at that case will be 40 cm plus 20 cm, which equals 60 cm. And also, if we need to install 3 cables, the trench width will be 40 cm plus 20 cm plus 20 cm, which equals 80 cm. So we can say that the formula used for the trench width equals 40 centimeter plus the number of cables minus 1, and all of that is times 20. So this is for the trench width and for the trench depth. Alright, now the next parameter we need to add to the trench is a break between each cable and the other, like that break here. So after each certain distance, we add a break between each cable and the other one. And the benefit of adding this break is to specify a straight path for the cable, so we need the cable to move on a straight path, not a curved path. And also we need the cables not to interfere with each other, or not to go through the other cable paths. So by that way we specify a particular path for each cable to go through. Alright. Now after installing the cables and the break, we set a layer of the white soft sand on the cables, and this layer has a height of 20 till 30 centimeters. So we add a specific type of sand above the cable directly, which is the white soft sand, and this sand height is about 20 to 30 centimeters. And after this sand layer, we add a brick layer to plug the trench totally, and this brick layer is used to protect the cables from any mechanical shock or from any stresses that may be applied to the cable. So this brick layer is considered to be the second layer. And after that, the third layer we add is the normal sand, and this normal sand is used to fill the trench until its end. So we end the trench with a layer of the normal sand. But when we are adding the normal sand layer, we add it with a warning tab, and this warning tab is added on about 30 centimeters from the top of the trench. So this warning tab is used as a warning that there are some cables that are inserted in this area. So if anyone is digging the trench again, he will see this warning tab on about 30 centimeters from the top of the trench. And here we will know that this is a dangerous area that has some cables installed on it. Very good. So we can summarize this operation of the properties of the trench in that we add firstly the cables on the trench, then we add the break between each cable and the other for the cable to have a straight path and a particular track. Then we add a layer of the white soft sand, and this layer is added on a height of 20 or 30 centimeters. And after this layer of the white soft sand, we add another layer of bricks to protect the cable. And then we fill the rest of the trench with a layer of the normal sand until the end of the trench. But on about 20 or 30 centimeters from the top or from the surface of the trench, we add a warning tab as an indication that there is a warning here, or this is a dangerous area that we need to avoid as it has some cables lays on it. Alright. Now you can ask, what if we need to check the cables that are installed underground as they are installed on a hole underground? So how can we check those cables for any reason? Suppose there is a fault in any cable of those cables, so how can we get this cable or how can we detect its fault? Here we say that on the trench we are not filling all of the trench with the sand, but there is a specific box or a specific room like that one here that is called the manhole, and this manhole is set with no filling. So it's a room or a box that has just a cover. And this manhole is used for a free access of the cable, so if there is any fault in the cable, we can open the cover of the manhole and we can check the cables directly as the manhole is just having a cover that covers the trench on its surface. And as we said, the manhole room is used for checking or inspecting or testing the cables. More than great. So that's about this tutorial at which we finished talking about the cables and the installation of the cables for their different methods of installing them. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In this tutorial, we will start talking about a new topic in the low voltage distribution system, which is the circuit breakers. So fasten your belt and let's get started. The aim of this tutorial is to learn about the idea behind the circuit breaker. So we need to know what is the working principle of the circuit breaker. And this is by knowing the behavior of the circuit breaker in the different cases inside the circuit. So let's go ahead. First of all, if we need to know what is the circuit breaker, we say that the circuit breaker is a protection device that is used to protect the circuit against any electrical fault, as there may be some different electrical faults that happens in the circuit, so we need to eliminate those faults, and this is done by using the circuit breaker. And the first type of faults we have in the circuit is the fault against the overload condition. And the overloading condition is a case at which the current passes through the circuit increases over the rated current with a significant value. And this significant increase in the rated current may damage the different parts of the circuit, as the electrical components are designed to withstand the rated current only. So when the current increases, this harms the circuit, and for that reason we need to protect the circuit by using the circuit breaker. For example, if this is a simple circuit that has this motor as an electrical load, and we have this 220 volt supplying source, so it works as a supplying source for the circuit, and we have this circuit breaker as a protection device. Now at the normal case, we find the motor to absorb a rated current of 9 ampere for example, and the circuit will work normally at that case with no problem. But suppose now any obstacle has been attached to the motor shaft by mistake. Now this obstacle will prevent the motor shaft from rotating with its rated speed, hence the motor will absorb more current than the rated current to overcome this obstacle that has been attached to the motor shaft. So at that case, the motor current will increase to P 10 ampere for example instead of the rated current of 9 ampere, and if this obstacle is still attached to the motor shaft, the current may increase also to P, for example 11 ampere instead of the normal rated current of 9 ampere. And this is what's called the overloading condition, which is an increase in the circuit current over than the rated current due to adding more loads to the circuit or due to an obstacle that is attached to the circuit load. But this increase in the circuit current to P 11 ampere for example will harm the different components of the circuit. For example, the electrical cables may be burned as it will not withstand this larger current, and also the motor itself may be heated and burned out as it will not withstand this larger current than the rated current. So it's designed to withstand a normal current of 9 ampere, and when the current increases by 2 ampere, the motor may be heated or burned out. And for that reason of the overloading condition, we come up with the idea of the circuit breaker, which will break the circuit in case of an overloading condition. As the circuit breaker internal structure has a bimetallic element, which is that part here, and the job of this bimetallic element is to trip the circuit in case of an overloading condition. So by tripping the circuit or opening it, the circuit breaker protects the circuit as it prevents passing a larger current than the rated current. Hence, we say that the overloading condition is a case at which the circuit current increases to P larger than the rated current, and at that case, the bimetallic element inside the circuit breaker is responsible for breaking the circuit. As the bimetallic element represents two different metals that are attached to each other, so they represent one part or one metal, and when the current increases over the rated current, this bimetallic element is heated due to the thermal effect of the increased current, and when the bimetallic element is heated, it will expand or its length will increase. So when the bimetallic element length increases due to the heating case, it forces the contact of the circuit breaker to break the circuit or to open the circuit breaker contacts. So this is the idea behind tripping the circuit breaker due to the overloading condition, which increases the temperature of the bimetallic element. Hence the bimetallic element expands, and when it's expand or when its length increases, it forces the contact of the circuit breaker to open or to trip the circuit. And this tripping time of the circuit breaker, or this opening time of the circuit breaker, is inversely proportional to the current passing through it. And this means when the overloading current increases, the circuit breaker trips the circuit much faster. And the inverse is right, as when the overloading current decreases, the circuit breaker trips the circuit, or its contact opens in a longer time. Also, this type of protection due to the overloading condition is called the thermal protection. This is because the circuit breaker trips the circuit due to the thermal effect of the bimetallic element, and the bimetallic element expands as a result of the thermal effect when a larger current passes through it. Very good. Now the second fault condition that may occur in the circuit, and we use the circuit breaker also to protect from it, is called the short circuit condition. And the short circuit condition is a condition at which there is a very large current that passes through the circuit. So at that case, there is no gradual increase in the circuit current, but the current increases very greatly at that case. And the reason that causes to the short circuit condition is that the line wire is connected by mistake to the neutral wire. For example, if we have this electrical load that has a resistance of 100 ohm, and it's supplied by this power supply that has a rated voltage of 220 volt, at that case, if we need to calculate the rated current that passes through the circuit at the normal case or at the healthy case, it will equal 220 over 100 ohm, which gives us a current of 2.2 amperes. Now suppose for any fault case, the line wire has been connected to the neutral wire, so this case represents a short circuit condition, and at that case approximately the total current will pass through this shorted wire, and approximately there will be no current passes through the electrical load. And this is because the wires are having a very small resistance with respect to the electrical load, as the resistance of the wires may be about 0.2 ohms, and the current prefers passing through the lower resistance, so all of the current passes through the wires and no current passes through the electrical load. And that's why it's called a short circuit condition. And if we calculated the short circuit current, it will be the voltage source of 220 over the short circuit resistance of 0.2 ohms. So it will give us a fault current of 1100 amperes. So you can see this is a very larger value of current that will burn the wires of the circuit, as it produces a great damage in the circuit. And for that reason, we use the circuit breaker, which is responsible for breaking the circuit in case of the short circuit condition. And this very huge current will burn the wires of the circuit, as it produces a great damage in the circuit. And for that reason, we use the circuit breaker that is responsible for breaking the circuit in this case of a short circuit condition. And the part of the circuit that is responsible for breaking the circuit in case of the fault condition is this magnetic coil. And the job of this magnetic coil is to open the contacts of the circuit breaker at the instance of passing a very large current through the circuit breaker. So we say that the short circuit condition is a condition at which the line and the neutral wires are shorted with each other, and those two wires can be a line and neutral, or they can be a line and another line, or a phase and another phase in the circuit. And at this short circuit condition, the magnetic coil of the circuit is turned into a temporary magnet, and this magnet attracts the contact of the circuit breaker to open it, hence the circuit breaker is broken. But this tripping of the circuit breaker at the short circuit condition is done instantaneously with no delay time, and this is done regardless to the value of the short circuit current. So at any short circuit current, the breaker will trip the circuit instantaneously with no delay time, so the short circuit is done instantaneously, or the tripping is done instantaneously. Also, this type of protection is called the magnetic protection, as at that case the coil is turned into a temporary magnet, which attracts the contact of the breaker to turn off the breaker at the instance of the short circuit condition. More than great. So that's about this tutorial at which we learned about the idea behind the circuit breaker and its principle of working. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In this tutorial we will continue talking about our new topic and the low voltage distribution system, which is the circuit breakers. So fasten your belt and let's get started. The aim of this tutorial is to know what is the characteristic of the circuit breaker. So we need to know how the circuit breaker can behave in the different cases, or we need to analyze the characteristic of the circuit breaker. And then we will start learning about the different types of circuit breakers we have, as each of them have some particular characteristic or they have some particular properties. So we need to know what are those properties or what are those different types of circuit breakers. So let's go ahead. First of all, if we need to express the circuit breaker characteristic as a relation between the breaking time and the current passing through it, we find that this is the relation between them. As you see on the x-axis we have the current passing through the breaker, and on the y-axis we have the time that the breaker will take to break the circuit. And this curve is the relation or the characteristic of the circuit breaker at the overloading condition. And you can see it's an inverse relation, which means when the overloading current passing through the breaker increases, the breaking time will decrease. And when the overloading current decreases, the breaking time will increase. For example, if we have this smaller overloading current, we find the breaker to break the circuit after a longer time. And if we have a larger overloading current value in the circuit, we find the breaker to break the circuit in a smaller time or in a smaller interval. And the more the current increases, the less the breaking time. So that's for the first part or the first section of the characteristic of the circuit breaker. Now the second part of the characteristic of the circuit breaker is the short circuit condition or the short circuit characteristic curve. And here it starts at the end of the overloading current and it ends at the maximum short circuit current that the breaker can withstand. So we can say that the first short circuit current value is the minimum short circuit current that the breaker will break the circuit at which instantaneously. And the last short circuit current is the maximum short circuit current that can pass through the breaker, or it's called the ultimate capacity current, which is the ultimate current that the breaker can withstand, or it measures the capacity of the breaker to break the circuit at the maximum current. And here the time t is a constant value for any short circuit current, and for any short circuit current between those two values, the starting short circuit current and the end short circuit current, at any value of them, the breaker will break the circuit instantaneously or with no delay time. So for the breaking time at this short circuit characteristic, we find the breaker to break the circuit with no delay time. So at any short circuit current, the breaking time is considered to be 0 time. This is because the breaker lasts no time to break the circuit, or it has no delay time before breaking the circuit. And this is the meaning of breaking the circuit instantaneously, as instantaneously means with no delay time. Very good. But for the short circuit current, we have two important short circuit values that we need to consider. The first one is the ultimate capacity current, and the second one is the service capacity current. And both of them are short circuit currents or values of current that the circuit breaker breaks the circuit at the short circuit condition. But for the ultimate capacity current, it's the maximum value of current that the breaker can break the circuit at but at the maximum short circuit current, the breaker may be damaged or not working well after passing this large short circuit current through it. So it's the maximum current that the breaker will withstand, but if this value of current passes through the breaker may not be used again or it may be damaged. On the other hand, for the service capacity current, it's not the maximum short circuit current, but it's a percentage of the maximum short circuit current or a percentage of the ultimate short circuit current. As the breaker can break the circuit at this short circuit current without being damaged. But if the breaker breaks the circuit at this value of current 3 consecutive times, there must be 3 minutes interval time between each breaking and the other. So this service capacity current is less value of current than the ultimate capacity current, or it's a percentage of the ultimate capacity current. But if the breaker breaks the circuit at the service capacity current 3 consecutive times, there must be a minimum time of 3 minutes between each breaking and the other for the breaker not to be damaged. For example, if we have a circuit breaker that has those 3 values written or at, here it's 630 ampere and 500 kiloampere, and ICS equals 50% of ICU. At that case, the first value is the rated current of the breaker, so this means that the breaker can withstand a rated current up to 630 ampere, and if a larger current than 630 ampere passes through the breaker, it will be considered as an overloading condition, and the breaker will break the circuit at which as an overloading condition. Then the second value is 50 kiloampere, which is the ultimate capacity current or the maximum current that the breaker can break the circuit at which, but if this value passes through the breaker, it may be damaged after this value passing through it. And then we have the service capacity current equals 50% of the ultimate capacity current, which means that the service capacity current of the circuit breaker equals 25 kiloampere. And this means that the breaker can break the circuit at 25 kiloampere with no problem or without being damaged. But if this value of 25 kiloampere passes through the breaker 3 consecutive times, there must be a minimum time of 3 minutes between each breaking and the other for the breaker not to being damaged or to work well. Also, we can have another breaker that has those data written on it. You can see it looks like the previous breaker exactly, except that the surface capacity current equals 100% of the ultimate capacity current. And this means that the breaker can work to tread the circuit at 50 kiloampere with no problem, or it will not be damaged. But if the breaker breaks the circuit 3 consecutive times, there must be a delay time between each breaking and the other of about a minimum time of 3 minutes. And the more the service capacity current increases, the higher price it will be, as it will be able to break the circuit at a higher or a larger current without being damaged. So we can conclude that breaker P has a higher price than breaker A, although both of them are having the same rated current and the same ultimate capacity current. But breaker P is having a larger service capacity current, so it's 100%, which is larger than breaker A, which has 50% only. Very good. Now we need to know what are the different types of breakers that we can select from. Here, the first type is called the miniature type, or the miniature circuit breaker, and this is the shape of the miniature circuit breaker. And this miniature circuit breaker has the smallest size, so its size is the smallest one related to the other circuit breakers or related to the other types of circuit breakers. And this means it will have the smallest rated current range also, as the ranges of current at the miniature circuit breaker starts at 10 ampere and it ends at 125 ampere. So the miniature circuit breaker can have some standard values in between those two values of 10 ampere and 125 ampere. So that's for the rated current, while for the short circuit current it ranges from 1k ampere till 15 kiloampere. So it has a capacity that ranges from 1000 ampere until 15 kiloampere. And for its breaking time, it has the smallest breaking time to be 3 milliseconds. Alright. Also, the next property of the miniature circuit breaker is that it's a fixed type circuit breaker, and this fixed type means that it has a fixed relation between the current and the breaking time, or it has the same relation of the overloading current or the short circuit current and the breaking time. And this means it will start breaking the circuit at a fixed current value, and it will end the overloading current region at a fixed overloading current value. And also it will start the short circuit characteristic at a fixed value, and it will end the short circuit characteristic at a fixed value. So we cannot offset the characteristic of the miniature circuit breaker, as it has a fixed characteristic related to each type of the miniature circuit breaker. Very good. Also for the miniature type circuit breaker, we have three types under it. The first one is P16, and this P16 circuit breaker has the smallest overloading margin, and it has the largest short circuit margin. And this means that the circuit breaker is a very sensitive one to any short circuit condition, as it starts to trip the circuit instantaneously at any smallest short circuit current. So it considers this smaller current to be a short circuit current, hence it trips the circuit at which instantaneously. And because the circuit breaker has the smallest starting from the short circuit margins, it's used in the sensitive applications or the sensitive loads at which we must trip the circuit at the smaller short circuit currents. So for the sensitive loads like some factories or the petroleum stations, we use this P16 type as it senses the smaller short circuit currents. Also, the second type of the miniature circuit breakers we have is C16 type, and at this type we have a medium starting for the short circuit curve, so we can see the starting of the short circuit region of the C16 circuit breaker is larger than the starting of the short circuit region of the P16 circuit breaker, and this means that the C16 circuit breaker is less sensitive in detecting the short circuit current, as it has a larger overloading margin and a smaller short circuit region. And for that reason we use it in the less sensitive loads, as it detects the short circuit currents at a larger value of current. Now the third type of the miniature circuit breakers we have is D16 circuit breaker, and at that type the circuit breaker short circuit margin is the smallest one, or it starts to trip the circuit instantaneously at a very large current. And this means that this type has a larger overloading margin, or it considers only the larger value of current to be the short circuit currents. And this type of circuit breakers is used for the non-sensitive loads or the non-sensitive applications, as this type detects the larger short circuit currents only. Very good. Also, we can categorize the miniature circuit breaker according to the number of poles of the circuit breaker. And for the number of poles, we have the single pole miniature circuit breaker, which is used to break the line wire only, like that one here. It's clear that it's a single phase circuit breaker. And also we have the double pole circuit breaker, and it's used to control the line and the neutral, and also it's used as a single phase circuit breaker. And the third type we have is the three pole circuit breaker, like that one. And at that case, this type is considered to be a three-phase circuit breaker, as it breaks the three phases, the R, the S, and T. Also, we have the fourth type, which is the four-pole circuit breaker, which is used to break the three phases R, S, T, and the neutral. And at that case, the input of the circuit breaker is the three phases and the neutral. More than great. So that's about this tutorial at which we illustrated the characteristic of the circuit breaker, and we started on illustrating the different types of circuit breakers. Hope that's clear right now. Thank you for watching, and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In this tutorial we will continue talking about our topic, which is the low voltage circuit breakers. So fasten your belt and let's get started. The aim of this tutorial is to continue learning about the different types of the circuit breakers. So let's go ahead. If you remember, in the previous tutorial we ended with the first type of circuit breakers, which is the miniature type circuit breaker. And now the second type of the circuit breaker we have is the molded case circuit breaker. And this type of circuit breakers has a medium size, so its size is larger than the size of the miniature circuit breaker. So its size is a medium size. And its rated current starts at 16 ampere and it ends at 1600 ampere. So we can have many standard value between those two values of 16 and 1600 amperes. And for the short circuit current of the molded case circuit breaker, it starts at 18 kiloampere until 70 kiloampere. Hence, we can buy a molded case circuit breaker with some standard ranges of the short circuit current between those two values of 18 and 70 kiloampere. And for the breaking time of the molded case circuit breaker, it's about 9 milliseconds, so it lasts a duration of 9 milliseconds to break the circuit. And now the important property of the molded case circuit breaker is that it can be a fixed type circuit breaker or an adjustable type circuit breaker. So we can buy a fixed type circuit breaker which has a fixed overloading current and a fixed curve for the short circuit current also. And this means we cannot change the time at which the breaker will trip the circuit for any specific current, or we cannot change the starting current of the short circuit region. So it has a fixed characteristic. But this type of circuit breakers can be adjustable also, and this means we can have an arrow in the circuit breaker to change the overloading curve or to offset the overloading curve to the right or to the left. And also we can have another arrow to change the overloading time up and down. And the same thing for the short circuit curve, we can have another arrow for the circuit breaker to change the short circuit current region right or left to increase the sensitivity of the breaker or to decrease the sensitivity of the breaker. So this third arrow is used to change the margin of the short circuit condition to increase the short circuit current or to decrease the short circuit current at which the breaker will trip the circuit. So it can sense the smaller short circuit currents only if we set the arrow to the left, or we can adjust it to sense the large short circuit currents only if we set this arrow to the right a little bit. As you see here, if we shifted the curves a little bit to the right, we are increasing the current at which the breaker will trip the circuit. And this is an example of adjusting the circuit breaker where we have 3 arrows on the circuit breaker and we can adjust each of them to the values that we need. As for the first arrow, it's used to adjust the overloading current curve to specify the value of current that the circuit breaker will tread the circuit at which as an overloading condition. And also the second arrow represents the short circuit characteristic or the value of the short circuit current that the breaker will start tripping the circuit at which. And the third arrow represents the overloading delay time. So by that arrow we adjust the delay time after which the breaker will trip the circuit. Hence, we can increase the delay time after which the breaker breaks the circuit, or we can decrease the delay time after which the breaker breaks the circuit at the overloading condition. And for the adjustable circuit breaker, we have 2 important parameters related to the adjustability of the overloading current. Here, the first parameter is the ampere frame. And this ampere frame is the maximum rated current value that the breaker is designed to withstand without breaking the circuit. For example, if we put a molded case circuit breaker with a rated current of 400 ampere, this means that this is the ampere frame of the circuit breaker to be 400 ampere, which means that the maximum rated current that this breaker can withstand is 400 ampere, and it will work well at any rated current value below 400 ampere. But if the current increases to be larger than 400 ampere, the breaker will break the circuit as an overloading condition because the current exceeds its maximum rated current. So that's for the ampere frame. Also, we have the ampere trip, which is the adjusted value that we set to trip the circuit at which. So this ampere trip is a percentage of the ampere frame. As if the ampere frame is 400 ampere, for example, we can set the ampere trip to be 300 amperes only to trip the circuit if a larger value than 300 ampere passes through the circuit breaker. And also another example, if we have an ampere frame for a circuit breaker of 630 ampere and we set the arrow at a percentage of 100%, at that case, the ampere trip will be 630 ampere also to get a percentage between the ampere frame and the ampere trip of 100%. But suppose we set the arrow on 90%, at that case, the ampere trip will be 570 ampere only, which means if the ampere passing through the circuit is larger than 570 ampere, the breaker will trip the circuit at that case. And also we can set the arrow on a value of 0.8 or on a percentage of 0.8, and this means we have a percentage between the ampere trip and the ampere frame of 500 over 630 ampere. So the breaker at that case will trip the circuit if a larger current than 500 ampere passes through the circuit. Alright, now for the types of the molded case circuit breaker, we have two types. The first one is the 3-pole molded case circuit breaker, at which the breaker is used to cut the three phases, the R, the S, and T. And also we can have the 4-pole molded case circuit breaker, at which we have four inputs, the three phases R, S, and T, and the fourth one is the neutral wire. So that's for the molded case circuit breaker. Now the third type of breakers we have is the air circuit breaker. And for that type of breakers, it has the largest size. As you see, its size is the largest one. And this is because it takes a larger range of its rated current. So its rated current starts from 630 ampere until 6300 amperes. So for the air circuit breaker, we can select any standard value that has a rated current or that has a standard rated current in between those two values. And for its short circuit current, it starts at 36 kiloampere until 150 kiloampere. So according to the maximum short circuit we have in the circuit, we can select the required value of the short circuit current we have from those standard ranges. And for its breaking time, it has the largest breaking time of about 30 milliseconds, so it breaks the circuit in about 30 milliseconds. And also this type of circuit breaker is an adjustable type circuit breaker, or it has no fixed circuit breakers. And this is because its rated current is a larger value, so we need to adjust it according to the loading condition of the electrical loads. As if there is an increase in the electrical loads in the future, or if there are some extensions in the electrical loads, we can increase the ampere trip value according to the rated current. So we can adjust the overloading current curve to have a value of current that we need to trip the circuit at which, and also we can adjust the overloading time to the required delay time value to trip the circuit at which. And the same thing for the short circuit current, we can adjust it to the required value of the short circuit current. But this is not only the characteristic we have for the air circuit breaker, as the air circuit breaker can have an additional characteristic like that one. Here we have the overloading current to be divided into two different curves. This first curve, which is called the long time delay, and this second curve, which is called the short time delay. And at the long time delay, the breaker breaks the circuit after a long time. But for the second one, which is the short time delay, the breaker breaks the circuit or trips the circuit at a smaller time or at a short time delay. And finally, we have the instantaneous characteristic, at which the breaker breaks the circuit instantaneously with no delay time. And at that case, we can have 5 arrows in the circuit breaker, or we can adjust 5 different parameters. The first one is used to adjust the long time over current, and the second one is used to adjust the long time, which is the time at which the breaker will break the circuit at the long over time, and the third arrow is used to adjust the short time short circuit current, and the fourth arrow is used to adjust the time of the short circuit current, or the short time for the short circuit current, and finally the fifth arrow is used to adjust the short circuit tripping current, or the instantaneous short circuit tripping current. And you can see we have here more arrows, so we have more flexibility, hence the price of the circuit breaker is larger than the price of the 3-arrow circuit breaker or the breaker with less flexibility. So we need to say that the more flexible circuit breaker, the higher price it will have. Very good. Now for the types of the circuit breaker or the types of the air circuit breaker, we have the 3-pole air circuit breaker, and also we have the 4-pole air circuit breaker. So for the 3-pole air circuit breaker, it will be used to control the 3 phases R, S, and T. And for the 4-pole air circuit breaker, it will be used to control the 3 phases and the neutral. Very good. Now we need to know what are the standard ranges of the circuit breaker that we can select from in the market. Here we say that we have many ranges of the circuit breaker that we can select from, and here those ranges are 10 ampere, 16 ampere, 20, 25, 32, 40, 50, 36, 80, 100, 125, 160, 200, 250, 320, 400 amperes, 500 amperes, 630 amperes, 800 amperes, 1000 amperes, 1025, 1060, 2000, 2500, 3020, 4000, 5000, and finally 6030 ampere. So that's for the rated current values. And also for the short circuit current values, they are 1k ampere, 3 kiloampere, 5, 6, 10, 15, 18, 20, 25, 70, 100, 130 kiloampere, and finally 150 kiloampere. So when we buy a circuit breaker from the market, we can select it from those rated current values, and also we can select it from those rated short circuit current values according to the maximum short circuit current we have and the position at which we will put this circuit breaker. Alright, now the important note we have is that suppose we have a main distribution panel that will feed a sub-main distribution panel. Here we will find that the ingoing circuit breaker and the sub-main distribution panel, it will have the same rating current of the outgoing circuit breaker in the main distribution panel. And this is because the same rating current will pass through the two circuit breakers. For example, if we have a rated current of the sub-main distribution panel of 200 ampere, we find a rated current of 200 ampere to go out of the main DP, and the same 200 ampere is going inside the sub-main DP. So the outgoing circuit breaker of the main DP will have a rated current of 20 ampere, and the ingoing circuit breaker of the sub-main DP will have the same rated current of 200 ampere. But you can ask now, what will change of those two circuit breakers? Here the only change is the short circuit current of the two breakers. As for the coordination purposes, if a short circuit happens on the sub-main DP, we need the lower circuit breaker or its ingoing circuit breaker to trip the circuit, not the upper circuit breaker or not the outgoing circuit breaker of the main DP in case of a short circuit condition. So suppose the short circuit condition has happened at this cable, we need the ingoing circuit breaker of the sub-main to break the circuit, not the outgoing circuit breaker of the main DP. And for that reason we select the upper circuit breaker with a larger short circuit current value, which may be for example 70 kiloampere, while we use the lower circuit breaker with a lower short circuit current value of about for example 25 kiloampere. This is for the lower circuit breaker to be more sensitive than the upper circuit breaker, hence it will take the action firstly to trip the circuit. So this coordination makes the nearest circuit breaker to trip the fault or to trip the circuit firstly before the farther circuit breaker. And the same idea if a fault happens at the outgoing of this submain circuit breaker or at one of its outgoings. At that case, this outgoing must trip the circuit firstly before this ingoing of this submain DP. And this is to maintain the power supplying to the other outgoings we have, as the other outgoings will still healthy, so there is no need to cut the power from them in case of cutting the ingoing of the submain DP, as we just need to cut the faulty circuit, not all the distribution panel, and this is what's called the reliability of the circuit or the reliability of the system, which is to maintain the power flow inside the circuit as much as possible, or for the most part of the circuit in case of it's a healthy circuit or a not faulty circuit. So just the faulted outgoing is cut. And for that purpose we get the short circuit current of the outgoing circuit breaker to be smaller than the short circuit current of the ingoing circuit breaker. This is for the outgoing circuit breaker to have a faster response to break the circuit in case of a fault happens on its circuit. Here we need it to break the circuit faster than the ingoing circuit breaker. More than great. So that's about this tutorial at which we continue talking about the different types of the circuit breakers. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In this tutorial we will start talking about a new important topic in the distribution system, which is the voltage drop calculations. So fasten your belt and let's get started. The aim of this tutorial is to know the idea behind the voltage drop and why it represents a problem in the low voltage distribution system. So let's go ahead. First of all, we need to ask an important question, which is that why we need to perform the voltage drop calculations, or why it's important to include the voltage drop as a factor inside the distribution system design. Here we say that each electrical device is designed to work on a specific value of voltage, and this device will produce the best output performance when its input becomes the rated voltage or the nominal voltage. For example, if we have this motor and it's ran on its nameplate a voltage of 220 volts and 1400 revolution per minute. This means that the rated input voltage of the motor is 220 volts, and when we supply this motor with this rated voltage of 220 volt, we will get the most optimum results of this motor as a rotational speed of 1400 revolution per minute. So this is the ideal case of the motor to give its highest performance or to give the highest efficiency by supplying it with its nominal voltage. And the same idea is applied to the electrical lamp, as if we supply it by a nominal voltage of 220 volts, it will give the best output performance of about, for example, 1000 lumens. As this lamp is working on its rated voltage of 220 volts to give the rated output results of 1000 lumens, for example. But suppose now this input voltage of the motor and the lamp has been decreased to be 180 volts instead of the 220 volts. Here at that case, the output of both of the electrical devices will be decreased greatly. So we will find that the motor outputs revolution per minute to decrease to be, for example, 800 revolution per minute instead of 1400 revolution per minute. But as the motor is designed to work on 1400 revolution per minute, so it will give a bad performance to work at 800 revolution per minute only, as when the motor is forced to work on a smaller speed, at that case its coils or winding will be heated and they may be burned out. Also, the lamp at that case may produce an output lumens of 500 lumens instead of the 1000 lumens, as each decrease in the input voltage by 1% will produce or will reduce the output lighting by 3%, which means that the output lumens of the lamp will decrease greatly, or the lamp will produce a bad performance and also the lamp may be burned out or damaged due to the decrease of the input voltage. So we can conclude that decreasing the input voltage of the device makes it to produce a bad performance, or they may be damaged as they are designed to work on the rated voltage. And for that reason, we must decrease the voltage drop as much as possible for the input voltage of the device not to decrease due to the voltage drop, as the voltage drop makes the device input voltage to decrease. Hence, the device will not work well when there is a large voltage drop, as the input voltage of the device decrease when the voltage drop increase. Very good. But you can ask now, what is the cause of the voltage drop, or what is the factor that leads to the voltage drop inside the distribution system? Here we say that the voltage drop occurs on the cables that are used to carry the electrical power. For example, if we have a single-phase induction motor that we need to feed with a supply of 220 volts, here we will use some cables to carry the power from the power source to the motor. So we can use two single-phase cables, one for the line and another one for the neutral. And at that case, if the motor position is far from the power source by 60 meters, for example, we will need a total cable length of 60 meters for the line and 60 meters for the neutral. And at that case, the total length of the cable of the circuit will be 60 times 2, which is 120 meters. But for any cable, there will be a resistance for the cable, and this resistance is represented in ohm per meter. And at that case, the cable resistance will be 0.12,000 ohm per meter. Hence, if we need to calculate the total resistance of this cable, it will be the total length of the cables per meter times the cable length, so it will be 120 times 0.12,000. And this will give us a total resistance of the cable of 1.44 ohm. Now, if we need to get the voltage drop across those cables, it will be the current passing through those cables times the resistance of those cables. And for the current passing through the cables, it's equal the rated current, which is the current that the motor absorbs. So suppose the motor absorbs a rated current of 9 amperes, for example. At that case, the voltage across the cables will equal 1.44 times 9 ampere, which gives a total voltage drop of 13 volts. And this voltage across the cable represents the voltage drop which we are working on, as the voltage that reaches the motor equals the input voltage of 220 volts minus the voltage across the cables. So the cable's voltage is about 13 volts, as we said. Hence, what reaches the motor now will equal the total input voltage of 220 volts minus 13 volt, which will be 207 volts only instead of the 220 volts. And this means that each cable will have a voltage drop of 6.5 volt, so the line cable will have a voltage drop across it of 6.5 volt, and the neutral cable will have a voltage drop of 6.5 volts. And we can conclude that the load voltage equals the input voltage or the source voltage minus the voltage drop. And as the source voltage has a constant value of 220 volts, so what leads to a smaller voltage drop is to have a smaller voltage drop across the cables themselves. As when the voltage drop increases, the load voltage will decrease. And this is an undesired case, as we said before, as it leads to a bad performance of the load, as the load is designed to work on a specific rated voltage. So if we need the load voltage not to decrease, we need to decrease the voltage drop as much as possible. So that's about the idea behind the voltage drop and what leads to the voltage drop. More than great. So that's about this tutorial, and on the next tutorial we will learn how to reduce the voltage drop and how to measure the voltage drop calculations. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In this tutorial we will continue talking about our important topic in the distribution system, which is the voltage drop calculations. So fasten your belt and let's get it started. The aim of this tutorial is to know how to calculate the voltage drop through the different parts in the distribution system we have. And then we will learn how to reduce the voltage drop to have a more stronger power system. So let's go ahead. First of all, we need to know how to make the voltage drop calculations and the practical design. Here we find the voltage drop calculation to vary according to the type of the electrical load. Is it a single-phase electrical load or it's a three-phase electrical load? As for the single-phase electrical load, we find the voltage drop to P equal the rated current of the electrical load times the resistance of the cable per kilometer, and we get this resistance from the cable data sheet, times 2 by considering the length of the line wire and the length of the neutral wire. As we consider that we have a cable for the line and a cable of the neutral, or by considering that we have a multi-core cable and this cable has two cores, one for the line and one for the neutral. So we get the length of the line and we multiply it by 2 as we have two conductors. So that's the first method for calculating the voltage drop in case of having the resistance of the cable. But there is another popular method for calculating the total voltage drop, and this is by getting the voltage drop through the cable in millivolt per ampere per meter. So we can get this value of millivolt per ampere per meter from the cable datasheet also, and at that case we multiply this value of millivolt per ampere per meter times 10 to the power minus 3 to get it in volts, times the rated current, as this is the volt per ampere. And finally, we multiply by the total length of the cable, which is 2 times the total length of each core, or for the line core or for the neutral core, for example, as we have 2 cores inside the cable, one for the line and another one for the neutral. So the final equation will be the millivolt per ampere per meter times 10 to the power minus 3 times the rated current times 2 times the cable length. So by that way we can calculate the voltage drop by its different two methods. And finally we can detect the voltage drop as a percentage of the total voltage, as we are not handling the voltage drop as a specific value of volt, but we are handling it as a percentage of the rated voltage of the system, or as a percentage of the system phase voltage. And we detect this percentage by dividing the voltage drop that we have just got over 220 volts, which is a single phase voltage. Alright, so that's for the single phase voltage drop calculations. Now what if we need to calculate the voltage drop of the three-phase load? Here at that case the voltage drop will equal the square root of 3 times the rated current times the resistance of the cable per kilometer times the total length of the cable. So this is the first method for calculating the three-phase voltage drop. Also the second method, if we are having the voltage drop of the cable from the data sheet of the cable to P in millivolt per ampere per meter, and by that way the total voltage drop will be the millivolt per ampere per meter times 10 to the power minus 3 to give the voltage in volt, not in millivolt, times the length of the cable in meter, as we have got the voltage drop in millivolt per ampere per meter. So if we get the voltage drop per meter, we multiply by the cable length in meter, as if we have got the voltage drop from the catalog per kilometer, we multiply by the length in kilometer, and if we have got the voltage drop from the catalog per meter, we multiply by the length in meter. So that's about the second method for calculating the voltage drop in case of having a three-phase electrical load. Also, after getting the voltage drop as a value in volts, we divide it over the phase voltage or the system voltage to get it as a percentage, or to get the voltage drop as a percentage of the system voltage. And here we have an example from the catalog data sheet, which we can use to detect the cable resistance in ohm per kilometer. As from this column we enter the table by the cable current, or the current that we have calculated that will pass through the cable, and we get the cross-sectional area of the cable from this column, and we detect the corresponding resistance of this cable from this column. Hence we calculate the voltage drop according to it. Very good. Now after knowing how to calculate the voltage drop, we need to know if this value of voltage drop is an accepted one or not. And for that, we have a standard value for the maximum allowable voltage drop percentage. As for the residential applications, the maximum allowable voltage drop percentage is 2.5%. So the maximum value of voltage that we must get must be less than or equal 2.5%. And this is in case of we are working on a residential electrical distribution application like the residential buildings or the distribution for homes. And on the other hand, if we are working on an industrial distribution application, the maximum allowable voltage drop must be less than 5%. And this means if we are working on a design of the distribution system for a factory, for example, we calculate the voltage drop through the different cables in this system, and this voltage drop at that case should be less than or equal 5%. Alright, but the important question now is that if we have calculated the voltage drop and we found it to be higher than the maximum allowable voltage, how can we reduce it? Or how can we solve this problem of having a higher voltage drop percentage? Here, if we need to adjust the voltage drop value, we need to adjust one of its factors that the voltage drop depends on. And as the voltage drop equals the current passing through the circuit times the resistance of the cable, so we find here the voltage drop to be directly proportional with the current and the time. And this means when the current increases, the voltage drop increases, and when the current decreases, the voltage drop will decrease. But actually, the current passing through the circuit is a constant one, as it's the rated current of the electrical load, or it's the rated current that the load will consume. Hence, we cannot adjust the rated current of this equation, or we cannot control this value of the voltage drop by controlling the rated current, as the rated current is a fixed value or a non-controllable value. And for that reason, we can only control the resistance of the cable, as if we manage to decrease the cable resistance, we can decrease the voltage drop across it directly. And because the cable resistance or the resistance of the conductor equals the resistivity of the conductor material times the length of the conductor over the cross-sectional area of the conductor. So if we control the length of the cable or if we control the cross-sectional area of the cable, we can control its resistance. And here, as the length of the cable is directly proportional to its resistance, so if we decrease the cable length, we can decrease its resistance. And by that way, we can decrease the voltage drop. So we can say that decreasing the cable length will decrease its voltage drop. And in the actual design, if we need to decrease the cable length, we need to change the position of the distribution panel to be more nearer to the electrical loads to connect between the distribution panel and the electrical load by a shorter cable, or not to have to use a longer cable as a result of having a larger distance between the distribution panel and the electrical loads. For example, if this is the layout of the floor that we will work on, and we have just an electrical room that lays at this position, and we need to connect between it and the electrical loads on the upper floor, and here we will need a longer cable which have a longer voltage drop, and this may be larger than 2.5%. And to solve this problem, we may use two different electrical rooms, one at the lower position of the floor and the other one at the middle position of the floor. And at that case, the lower room will feed the lower electrical loads, and the middle room or the middle distribution panels will feed the upper rooms and the lower rooms on the other side. And as a result, we will need shorter cables, or the length of the cables will be smaller. Hence, the total voltage drop will decrease as the cable length has been decreased. So this is the first way to reduce the voltage drop by decreasing the cable lengths. Alright, now the second method of decreasing the voltage drop is used by increasing the cable cross-sectional area, as the cross-sectional area of the cable is inversely proportional to the cable resistance, which means when the cable cross-sectional area increases, its total resistance will decrease. And the inverse is right, as when the cable cross-sectional area decreases, the total resistance of the cable will increase. So if we find the voltage drop across any cable to be larger than 2.5%, we can increase its cross-sectional area, and then the voltage drop will be decreased. For example, if we calculated the cross-sectional area for a lighting circuit, and we found that we need 3 single core cables, and each of them has a cross-sectional area of 2 mm square, so we need 3 times 2 mm square single core cables, but the voltage drop across those cables is larger than the acceptable value of 2.5%, for example. At that case, we can increase the cable cross-sectional area to be 3 times 3 mm square. And by that way, we can reduce the voltage drop by increasing the cable's cross-sectional area. So we make the calculations again and check the voltage drop. And if we found that it's in the acceptable range or it's in the acceptable percentage, we will accept the design. Very good. So that's for the factors by which we can reduce the voltage drop across the cables. Now the final note we have is that the voltage drop is calculated across all the cables we have in the network, and we get the sum of the voltage drop across all the series cables in the network. For example, if we have this low voltage network or this low voltage distribution electrical network, and we need to calculate the voltage that reaches this load, for example, at that case we will sum all the voltage drop values across all the cables we have, starting from the transformer ending at the electrical load we have. So the total voltage drop will be the voltage drop across this cable plus the voltage drop across this cable plus the voltage drop across this cable plus the voltage drop across this cable. So you can note that we start from the transformer and we are adding all the series cables until the load that we need to calculate the voltage drop at which. And also another example, if we need to calculate the voltage drop across this electrical load or the voltage percentage that reaches this electrical load, at that case we will add the voltage drop across this cable plus the voltage drop across this cable and finally plus the voltage drop across this cable. So that's for detecting the total voltage drop for any load that we have globally in the electrical network. More than great. So that's about this tutorial at which we continue talking about the voltage drop calculation and reduction. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we are all together again. In this tutorial we will start the first step in designing the single line diagram for any electrical distribution network we have, and we will do this practically using the ETAP software. As when constructing the electrical network, we will be capable of making the voltage drop and the short circuit calculations, and all of those calculations will be very easier with programs like ETAP, as we avoid the manual calculations at those conditions, as the manual calculations are very tiring and it lasts much step, and we are exposed to make some mistakes while doing the manual calculations. So let's start now with the ETAP calculations. First of all, after downloading and installing the ETAP software, you will find that this is the ETAP icon, or this is the shortcut for the ETAP icon that we will use to access the ETAP software. And you can find it on your desktop, and if you didn't find it in your desktop, you can search in your PC for it by typing on the search bar ETAP. So let's press a double click on this ETAP icon to open it. Here it's loading. Now you can see this window gives us some options that we can select from. Here we can open some examples that the program is preparing initially and we can use to work on. But as we need to design a new project from scratch, so we can open this new example by pressing double click on it. After that we press on OK and then OK, and here it's loading. Now you can see this is the initial window for the software or for the ETAP software that we will work on. And here this smaller window is the window that we use to design our project or that we use to draw the components of our distribution network. So we need to maximize it by pressing on this button. That's great. You can see the window has been maximized and we can draw our project at this area. Now we can find that this is the initial interface for the ETAP program. And here on the right columns, we have the different electrical components that we can pick from to build our electrical distribution network. For example, this is a sample for a 2-winding transformer. So this is the distribution transformer that we can use. And this is a sample for the cable. So we can pick a cable to connect between the transformer and the distribution panel, for example. And here, this is the sample for the power grid or the power utility that we can use to feed our transformer from the medium voltage side. And for example, this is a sample for an induction motor. And here, if we go down, we can find that this is the sample for the low voltage circuit breaker and so on. So that's for the components that we can pick from to build our project here on those right columns. Also, we have those rows on the upper side, which are having the actions that we can perform on the power network. So those tabs represent the processes that we can perform on the power network, or they represent the different operations that we can apply on the network to analyze it well. For example, this tab, which is the pen mode, is used to edit the project. So we are now on the edit mode, at which we can select the components that we need for our distribution network, and we can connect between them to draw our network we need. So that's for the edit mode. Also, we have this load flow mode, and we use this load flow mode to perform the voltage drop calculations. And here we have another mode, which is the short circuit mode, and we use this short circuit mode to make the short circuit calculations or to check the maximum values of the short circuit current through the different parts of the network. And here, this is the harmonic mode, at which we can check the harmonic on our system. And here, this is another mode, which is the transient stability. And we can use this transient stability to check the stability of the system at the transient condition or at the starting or the termination of our network, or at the starting condition of our network. Alright, and because now we need to draw our network firstly, so we will select this edit mode, so we will be at the edit mode to draw our network. But the first important step now we need to do before designing the network is to check the units and the standards that we are using in our system that we will work according to. So we need to know, is it the international standard IEC, or is it the national standard NEC, and so on. And to do so, we go to this project tab and press a left click on it, and then we press on standards. Alright, you can see this window pops up for us. And here we can select the standard from this tab. Here it's set initially on the ANSI standard, but as we need to work on the IEC standard, so we will select the IEC standard. And also for the frequency, we will select the 50 Hz frequency or the 50 Hz system, as we will work on the 50 Hz system. And the same thing for the unit system. So at this part or at this tab, we can select the units that we will work on. So we need to work on the metric system, not the English system. And for that, we will select the metric system. And then we press on OK. Very good. After that, we close this tab by pressing on OK. Alright. Now you can note that those samples here on those columns has been changed, as they have been changed to the IEC samples and instead of the NEC samples, as each standard has its own samples or its own shape of samples of the different electrical components. Alright, now we are ready to design our electrical distribution network, and the first part of the network is the utility or the medium voltage grid that will feed the transformer from its primary side as a medium voltage source. So we will go to this grid tab and press a left click on it. And here we can drag it to insert it at this position, for example. And because this grid will feed the distribution transformer through the ring main unit or through the load break switch, so we need to insert a bus bar that will represent the copper bus bar of this ring main unit. So to insert the taskbar, we go to its sample here and press a left click on it. And here we can drag it to paste it at this position, for example. After that, we need to insert the 2-winding transformer that will transfer the electrical power to the distribution network. And for that, we go to this sample, which is the 2-winding transformer. We can press a left click on it. And here we pick it with the mouse to insert it at this position. Very good. And now we need to adjust the width of this taskbar. So we need to increase the length of this ring min unit or this taskbar for this ring min unit. And here we can press on it and go to this position until this arrow appears for us. And then we press a left click and then we drag while pressing a left click. You can see we are extending the length of this taskbar. Very good. Now we can reposition it by centering it at this position. Very good. After that, we can select it, and here we need to increase its thickness. So we press a right click on it, and then go to the thickness tab, and let's select the thickness to P5. So we are increasing the thickness of this taskbar. Very good. Also, to connect between the grid and this taskbar, we can go to the end of this grid. You can see this point pops up for us. So we press a left click and we drag down here until reaching the taskbar. So we have connected the grid to this ring min unit, and the same thing we can connect between the transformer and this ring min unit, and this is by pressing also a left click and going up until reaching the taskbar. Alright, now the next step we need to do is to draw the main distribution panel that will be fed from the transformer. And because any distribution panel is just a taskbar that has an input circuit breaker and some output circuit breakers, so we can insert another taskbar that will represent the main distribution panel. But not to repeat those actions again by going to this tab and inserting a taskbar, we can easily copy this taskbar of this ring min unit and use it as the main distribution panel taskbar. So if we select it and press a right click and then copy, and then we insert another right click and then paste, you can see we have pasted our taskbar here, or this taskbar will represent the main distribution panel we have. Now let's connect between the transformer and it. So we drag down until reaching this taskbar. Alright. Now we can suppose that this main distribution panel is feeding two sub-main distribution panels, and for that purpose we can copy this main distribution panel and paste it down here and there 2 times to insert the 2 sub-main distribution panels. And for that we can select it and press Ctrl C to copy it, and then press Ctrl V. So we have inserted the first sub-main distribution panel, and then press another Ctrl V to insert the other sub-main distribution panel. Here we insert it at this position. Very good. Now to connect between this main distribution panel and those 2 sub-main distribution panels, we cannot connect between them directly, but there must be some means of cables that will transfer the power from this main distribution panel and those 2 sub-main distribution panels. As the main distribution panel and the sub-main distribution panels are not at the same positions, so we need to link between them with some types of cables. And this is because there is a considerable distance between the main distribution panel and the sub-main distribution panel. For example, the main distribution panel may be in the ground floor, and the first sub-main distribution panel may be in the first floor, which is far from the main distribution panel with 10 meters, for example. And the second sub-main distribution panel may be in the 3rd floor, so it may be far from the first main distribution panel with 30 meters. And for that purpose, we will go to the cable sample. Here we press a left click on it, and we can insert it at this position, and we can copy it by selecting it and pressing Ctrl C and then Ctrl V. Then we can drag the second cable and insert it at this position. Very good. Now what we will do is to link between the main distribution panel and the first sub-main distribution panel, And we will do the same thing by linking between the main distribution panel and the second sub-main distribution panel. So we can go to this point and drag up while reaching this point for the main distribution panel. And here let's drag this cable, and we will do the same thing. Here we connect it to this point and then connect it to this point. Now let's increase the distance a little bit by dragging this sub-main distribution panel down, and then we drag this cable down, and also we drag the sub-main distribution panel down, and also we drag this cable down a little bit. And here let's drag this wire to the left a little bit. Very good. Also we need to insert an ingoing circuit breaker for the main distribution panel and some outgoing circuit breakers to the other distribution panels. So to insert the circuit breakers, we go to the sample, which is the low voltage circuit breaker, and then we press a left click on it, and here we insert it as the ingoing for this main distribution panel. And also we can copy it by pressing Ctrl C and Ctrl V, and also we can insert another low voltage circuit breaker, and here we insert it as the outgoing of this main distribution panel, and we insert another one for the other sub-main distribution panel. Very good. Now what we need to do is to insert the electrical loads that each of those sub-main distribution panel will be feeding, as this distribution panel will be feeding some electrical loads, and this sub-main distribution panel will feeding some other electrical loads. And for the electrical loads, we have two types of them. The first one is the static electrical loads, and the static electrical loads are the loads that are absorbing a fixed value of electrical current during the time. So it's a stable load or it's a static load. Like the lighting loads, for example, they are absorbing a constant value of current during its working time. And also the second type of loads is the lambda load, which is a combination of the static load and the dynamic load. And this dynamic electrical load is a varying electrical load that absorbs a variable electrical current during the time, or it absorbs a non-constant electrical load during the time. And for that purpose we have those two samples here. The first one is the static load, and the second one is the lambda load, which consists of the combination of the static load and the varying load. So let's select this static electrical load, for example, and here we can insert it to this sub-main distribution panel, and we can insert a cable to connect between the sub-main distribution panel and this load. So we connect this cable to this load, and also we connect this cable to this sub-main distribution panel. And suppose now this sub-main distribution panel is feeding another sub-main distribution panel. So this panel is feeding another panel. And for that we can select this bus bar and then press Ctrl C and then Ctrl V. And now we can drag this another sub-main distribution panel down here. And then we need to insert another cable. So we insert a cable at this position to connect between the upper panel and the lower panel. And also we can suppose that this sub-main distribution panel is feeding another static load. So we can go to the static load again and select it and paste it at this position. And then we can connect between this static load and this electrical panel. Also we need to insert a cable that will link between the sub-main distribution panel and this load, as this load isn't at the position of this distribution panel, so it's far from this distribution panel. Hence we can select this cable and we can insert it at this position. Alright, now what's remaining for us to finish this network is to insert the electrical load that will be fed from this left sub-main distribution panel. And for that we can suppose that we have a lambda load that will be fed from this sub-main distribution panel. So we can insert this lambda load here, and then we insert a cable at this position. So let's drag this load down and drag this cable down and connect between this cable and this sub-main distribution panel, and connect between this cable and this lambda electrical load. Very good. Also we need to insert the ingoing circuit breakers and the outgoing circuit breakers for those three distribution panels, we have this one and this one and this one. And for that, we can select another low voltage circuit breaker and position it as an input for this submain distribution panel, and also select another one and position it as the outgoing for this submain distribution panel, and a third one as an outgoing for the other branch of this submain distribution panel. And here for this lower submain distribution panel, we insert an ingoing circuit breaker. Here we insert it at this position, and let's drag it down, and also insert another one as its outgoing. And the same thing for the last distribution panel we have. We insert its input or its ingoing circuit breaker, and we insert its outgoing circuit breaker at this position. So by that way, we have ended the construction of the electrical distribution network we have. More than great. So that's about this tutorial, and on the next tutorial we will start on designing the different parameters of the network that we have entered, and this is by entering the required data for each element of this network we have. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. I'm very happy that we're all together again. In this tutorial we will continue talking about the designing of the electrical distribution network we have to get a complete network that we can analyze and apply the different power operations on it, like the voltage drop and the short circuit calculations. So let's start. First of all, we need to start with the first element in the network we have, which is the electrical grid from the medium voltage side, as we need to enter its required electrical data. And for that purpose, we can press a double click on it, and here you can see this initial window pops up for us. So at this window, we will enter the ratings of the medium voltage grid. So let's press on the second tab, which is the rating tab. Here we can enter the rated voltage of this network. So it can be 11 kilovolt or 22 kilovolt and so on, as we said before. But for us now, we can suppose that it's an 11 kilovolt network. So let's make the rated voltage to be 11 kilovolt. And after that, we need to enter the megavolt ampere of this network, or the short circuit power for this network. And because it's an 11 kilovolt network, so its megavolt ampere short circuit will be 500 megavolt ampere, as we said before, while if it was a 22 kilovolt network, we will enter its megavolt ampere to be 750 megavolt ampere. So let's enter it now to be 500 megavolt ampere, and for that purpose we will go to the third tab, which is the short circuit tab, and then we enter the megavolt ampere to be 500 megavolt ampere. And also the third parameter we need to enter is the X over R ratio. And as we said before, we get this value from the utility of the grid that we are getting the electrical power from. And for us now it's equal 10, so let's select it and specify it to P10. Very good. So that's all the required designing data for the grid we have. And after entering them, we can press on OK to close this tab. And now let's move to the second element we have in the network, which is the ring min unit or the busbar that will feed the transformer. So let's press a double click on it. And here what we need to enter for this busbar is just the rated voltage. And this rated voltage is set automatically to P11 kilovolt, as you see. And this is because this busbar is connected directly to the grid. And we have entered the grid rated voltage to be 11 kilovolt. So the busbar rated voltage changes automatically when changing the rated voltage of the grid. And hence we have entered it, so we press on OK. And now the next component we have is the transformer. So we press a double click on it. And here this initial window appears for us for the transformer. But we need to enter the rating of the transformer. So we can press on this rating tab. And now the rated primary voltage of this transformer is 11 kilovolt. So it's set automatically to be 11 kilovolt. As we said before, it's connected directly to the grid. And we have entered the grid rated voltage. So the transformer is linked to it, and its value of rated voltage will change automatically by changing the grid rated voltage value. So that's for the primary rated voltage. But for the secondary rated voltage, it's a standard value of 0.4 kilovolt. So we select it to be 0.4 kilovolt, which is 400 volts. And also we need to enter the rated power of this transformer. So we can suppose that this transformer has a rated power of 300 kilovolt ampere. And for that purpose, we can change this megavolt ampere to P kilovolt ampere. And then we change the rating to P 300 kilovolt ampere. Very good. After that, we need to enter the third tab, which is the impedance tab. So let's access this impedance tab. And here we need to set the per unit impedance of this transformer. This is, as we said before, we enter this value from the datasheet of the transformer or from its nameplate. So let's suppose now the Z percentage of this transformer is 4%. And also we need to enter its X over R ratio. So we can set it to P10. Here this is the X over R ratio for this transformer. Alright. So that's for the important designing data for the transformer. Now we can close this tab by pressing on OK. Also, the next element we have is the main distribution panel, which is represented by this busbar. And because we have set the secondary rated voltage of this transformer to P400 volts, so when we access this main distribution panel, we can find that its nominal voltage or its rated voltage is 0.4 kilovolt or 400 volts. This is, as we said before, its rated voltage changes automatically by changing the rated voltage of the component which is connected to it, which is this transformer at our case. So we don't need to enter it again, or we don't need to access any other busbar, as all busbars will have the rated voltage of the secondary voltage of this transformer, which is 400 volts. Very good. Now we press on OK. After that, what we need to do is to enter the required designing data for this cable. So let's press a double click on it. Here the first parameter we need to enter is the cable length. And as we said before, the cable length depends on the distance between the different distribution panels which we use the cable to link between. So we can suppose that the distance between this main distribution panel and this main distribution panel is 10 meters. Hence we can make the unit of the length to P meter, and then we can insert it, or we can select it to be 10 meters. Very good. Now the next parameter we need to enter is the number of conductors per phase, and this parameter is used to select the number of parallel cables we have, as we can use 2 or 3 parallel cables to connect between the same load. So this cable here may be 2 or 3 cables that are connected in parallel to connect between this main distribution panel and this main distribution panel. And we use those parallel cables because we cannot have an available larger cross-sectional area of the cable. So we have to use a parallel cable to increase the total cross-sectional area in case of having a single cable that has a lower required cross-sectional area. For example, if we calculated the total cross-sectional area and we found that we need a 200 millimeter square cable, but at the same time this cable of 200 millimeter square is not available in the market, at that case we have to use 3 parallel cables, and each of them has a cross-sectional area of 70 millimeter square. Hence, the total cross-sectional area will be 210 millimeter square, which is sufficient at that case. But for us now, we can suppose we are using 1 conductor or 1 cable, or we have no parallel cable. And for that, we set the number of conductor per phase to be only 1. Also, if we need to insert the other parameters of the cable, like the conductor material, is it copper or aluminum, or the conductor inner insulation, is it PVC or XLPE, and for the rest of the parameters we have, we can open this library tab. As using this library, we can select the different parameters of the cable. For example, this is a cable that works on a frequency of 50 Hz system, and it's of the aluminum type, and it can withstand a maximum voltage of 0.6 kilovolt, and its insulation material is the rubber material. So this is one selection that we can use, but for us now we will select this cable as it also an aluminum cable, but it can withstand a rated voltage up to 1 kilovolt. This is because we are working on the low voltage side, not the medium voltage side, so we need two cable to withstand a maximum voltage of about 1 or 1.2 kilovolt as we said before. Alright, now what's remaining for us is the cable cross-sectional area. So we can suppose that we have calculated the required cable cross-sectional area previously according to the rated current that will pass through this cable, and we found that this cable needs a cross-sectional area of 95 millimeters square. So we can select the cable cross-sectional area from this tab down here, but here we have two options to select from them. The first one is the available size, and the second one is the all sizes option. And we select the first selection, which is the available sizes, if the neutral cross-sectional area is half of the face cross-sectional area, or we are working on the reduced neutral case. And also we can use the second selection, which is all sizes, if the neutral cross-sectional area has the same cross-sectional area of the three phases. But as the cable cross-sectional area now is larger than 25 millimeters square, so we can use the reduced neutral option or the available sizes option. And here, after selecting this option, we can select the cable cross-sectional area to be 95 millimeters square, and then we press on OK, and then we press on OK. So that's for the first cable. Here we have managed to enter its required designing data. Very good. Now we will repeat the same idea with the rest of the cables. We have this cable and this one and the third one and this fourth cable and this fifth cable. So let's access the second cable, for example, and we can suppose its length is 15 meter, so we can change this unit to p meter, and here we make this length to be 15 meter, and then we open the library, and now we can change the selection of the cable to be this one as we said before. And for the cable cross-sectional area it's 16 millimeters square, but we will use the all sizes option. This is because the cable cross-sectional area of 16 millimeters square is smaller than 25 millimeters square, so we will not use the reduced neutral option, or the three phases will have the same cross-sectional area of the neutral. Hence we will use the all sizes option, and then we select the selection of 16 millimeters square, and then we press on OK, and after that we press on OK. Very good. Now we have this third cable. We press a double click on it, and here we can suppose that this cable length, which links between this submain distribution panel and this submain distribution panel, is 10 meters, and this is by supposing that this distribution panel is far from this distribution panel by 10 meters. So we can change the unit to p meter, and then we make the length to be 10 meters, and then we open the library, and here we select this cable, and for its cross-sectional area when designing it we found it to be 35 millimeters square, and as 35 is larger than 25 millimeters square, so we will use the available sizes option. This is by supposing that the neutral is a reduced one, or it's a reduced one, so we can select the 35 millimeters square, and then we press on OK, and then OK. Alright, now for the last cable we have, we can open it, and let's drag the tab to the left a little bit, and for its length we can suppose it to be 12 meters. This is by supposing that this electrical load is far from this distribution panel by 12 meters, and here we can select this feet to p meter, and then we open the library, and on the library here we can select this cable to be the aluminum one, and for this cable it will have the same cross-sectional area of the previous one of 35 millimeters square. This is because this cable has the same rating current of this cable, so the same current that will pass through this cable will pass through this cable, as those two cables are feeding the same load, which is this electrical load. So we select also this option, which is the available sizes, and then we select 35 millimeters square, and then we press on OK and OK. Alright, now let's move to this fifth cable, and here we can suppose its length to be 30 meter, so we can select it to be 30, and here meter, and then we open the library and select the same cable, and for its cross-sectional area we can suppose it to be 240 millimeters square, so we can go down and select this 240 millimeters square, and then press on OK, and then press on OK, and the same thing for the last cable we have. We can access it and select its length to be in meter, and here for its length it's 20 meter, and we can open the library and we can select our cable that we have used, and for its cross-sectional area it will be the same thing for the previous one. Here it's 240 millimeters square, as the same current will pass from the upper cable to the lower cable, so they are having the same rating current and the same rating cross-sectional area, and then we press on OK and then OK. Alright, now what's remaining for us is to enter the data of the electrical load, this static load and this static one and this lambda electrical load. So let's press a double click on this electrical load, and here this initial window pops up for us to enter the basic information of the electrical load, and then go to the loading tab, and it changes power to P in kilovolt ampere, and now let's change it to P 60 kilovolt ampere, so we can suppose that this load has a total electrical power of 60 kilovolt ampere, and for its power factor it's also 85%, and then we press on OK. And finally, we have this final electrical load, which is this lambda electrical load. We can press a double click on it and go to its nameplate. And then we need to enter its rated power, so we can change it to P in kilovolt ampere. And now we can suppose it to be 130 kilovolt ampere. And here, using this variac, we can select the static part of the load and the dynamic part of the load. So when dragging this variac to the right, we are increasing the constant load or the static load, and when dragging this variac to the left, we are decreasing the constant load or the static load. So let's make it to be a static load with 40%. Here, by adjusting this 40%, this means that 40% of the load is a constant one or a static load, and 60% of the load is a dynamic electrical load. Alright, now we can press on OK. That's good. So that's for entering or designing all the parameters we have for all of the electrical components in this electrical distribution network. And on the next tutorial, we will continue designing the electrical network to perform the voltage drop and the short circuit calculations. More than great. So that's about this tutorial. Hope that's clear right now. Thank you for watching and see you in next tutorials. Hello and welcome everyone. We're happy that we're all together again. In this tutorial we will continue talking about the electrical distribution design using the ETAP software. So let's start. Now the next step we need to do is to perform the voltage drop calculations. And to do so we need to go to the power flow mode. So we press on this second tab, which is the power flow tab. Here we are on the load flow mode, and we are ready to check the voltage drop results. So what we will do now is to press on this tab here on the right, which is the run load flow. So by pressing on this tab, we will run the load flow mode. Here we press a left click on it. Alright, as you see here, the values in percentage written on the red here and there are the voltage percentage values at those bus bars. And we can zoom in a little bit by pressing on this tab or this zoom in tab, and then we can drag to this part. As you see, the voltage level at the grid is 100%, which means that there are no losses at the grid. And this is a logical thing because at the grid you get the total voltage you need, or there are no losses in the power, hence there is no voltage drop. So we have a 100% of voltage, which means that there are no losses at this bus bar. And you can see here the rated current is 11.4 ampere. This is because we are at the medium voltage side, which has a larger voltage rating of 11 kilovolt. So when the voltage increases, the current decreases to be only 11 ampere. But here when going down after the transformer, we can find that the current increases. So the total rated current consumed by this transformer at the low voltage side is 313 ampere. And this is the larger value because the voltage has been decreased to be only 400 volt. So the transformer steps the voltage down and it steps the current up. And here at this bus bar you can see the rated voltage is 98.22, which means we have about 2% of voltage drop at this bus bar or at this transformer. Also we can go down to see the voltage level at the other bus bars. So when going down, we will find that at this distribution panel, we have about the same voltage drop of 98%. So the voltage drop across this cable is very low. Hence, we have a total voltage drop at this bus bar of about 2%. While when going down a little bit, we can see the voltage drop at this bus bar is about 2.5%, as the voltage level that reaches this bus bar is 97.6%. Hence, the total voltage drop at this bus bar is about 2.5%. And you can see the rated current that this electrical load absorbs is 94.2 ampere. And it's the same rated current that passes through this cable of 94.2 ampere. And for that reason, we have entered the same cross-sectional area of this cable to be the same one for this cable. This is because we have the same rating current passing through this cable and this one. While for this cable we have a rated current of about 42.2 ampere. Alright, now let's move to the second branch. Here the voltage drop at this bus bar is about 2.3%, as the voltage level is 97.7%. So it's an accepted value also. This is because, as we said before, if the voltage drop is between 0 and 5%, it will be an accepted value. While if the voltage drop increases to be larger than 5%, it will be a non-acceptable value, and we need to change it, or we need to modify the parameters that affects the voltage drop to decrease the voltage drop. Alright, now let's zoom out a little bit. Here we can zoom out. Alright, now we can try changing the parameters which affects the voltage drop calculations to see practically how the voltage drop changes by changing its parameters. So for that purpose we can go back to the edit mode, and now suppose we have access to this cable again, and here if we increase its length greatly to be, for example, 70 meter, if you remember, as we said before, when the length of the cable increases, the voltage drop increases. So let's see what will happen when increasing the length of the cable. Here we press on OK, and then we go to the power flow mode again, and then we run the load flow mode. Alright, you can see here when increasing the cable length, the voltage drop has been increased, as the voltage drop here has been increased from about 2% to be about 4%, as the voltage level has been decreased here to be 95.7%. Now we can close the load flow again, and here we go back to the edit mode. Also, the second parameter that affects the voltage drop calculations is the cable cross-sectional area. So if we access this cable, now we can return its length back to be 10 meter, and then we go to the cable cross-sectional area. So we open the library and select the cable cross-sectional area to be, for example, 6 millimeters square, and then press OK, and then we press on OK. And now we run the load flow calculations again, and then open the load flow calculations. Very good. So we have a voltage level of 86.3%, which is a very low value of voltage. Hence, this electrical load cannot work at this voltage level as it's a very smaller value. So this is the effect of changing the cable cross-sectional area and its length on the voltage drop calculations. And here we can note also the busbar color has been changed to be the red color, as the program has three colors represents the voltage level of the different busbars. The first one is this black color, which means that the voltage drop is less than 2.5%, and this magenta color, which means that the voltage drop level lies between 2.5% and 5%, which is an acceptable value also, and this red color, which means that the voltage drop is larger than 5%, so it's a non-acceptable value, and we must change the parameters of the cables we have to decrease the voltage drop. Alright, now let's move back to the edit mode, and then let's return this cable parameters back. So its length is 10 meter, and for its cross-sectional area it was 35 millimeters square, and then press OK, and then press OK. Now the next calculations we need to perform is the short circuit calculations. And to apply the short circuit calculations, we easily press on this tab, which is the short circuit tab, and then we need to include all the busbars we have in the short circuit calculations, as the short circuit is done on the busbars. So for doing so, we can press on this package tab, and then we have all of those busbars and the network. They are at this area, which is the done fault area, or we cannot checking their fault current when they are at this area. So we need to fault all of them, or we need to path all of them to the fault area. Hence, we can select all of the busbars and then press on this tab, which is the fault tab, to add all of the busbars to the fault area. So we press on fault, and here by that way we can make the short circuit calculations on all of the busbars we have. Then we press on OK. You can see all of the busbars color has been changed to the red, and this is an indication that all of the busbars will be included in the short circuit calculations. Very good. Now to run the short circuit calculations, we press on this tab, which is the duty tab, or to run the short circuit calculations. Very good. You can see the short circuit current at this busbar is 26.7 kiloampere, which means that we have a maximum short circuit current at this busbar of 26.7 kiloampere. And for this busbar after the transformer, we have a short circuit current of 11.2 kiloampere, which means that this busbar and this outgoing circuit breaker and this ingoing circuit breaker, all of them must have a short circuit capacity that is larger than 11 kiloampere. So when pieing this circuit breaker, we will pie it with a short circuit capability of about 15 kiloampere. So its short circuit capacity will be 15 kiloampere, which is larger than 11 kiloampere, as if the short circuit has occurred at this busbar with its maximum value, all the circuit breakers at this distribution panel must withstand this short circuit current or not to be damaged when this maximum short circuit current passes through this distribution panel. And also when going down, we will find that we have a short circuit current of 10 kiloampere at this busbar, and for that purpose we get this circuit breaker with a short circuit capacity of 15 kiloampere also, and the same thing for those two outgoing circuit breakers. And when going down, we will find that the short circuit current has been decreased to P 8.4 kiloampere, which means that for this distribution panel, we can pie the circuit breaker with a short circuit current of 10 kiloampere, as 10 kiloampere short circuit capacity of this circuit breaker will be capable of withstanding this maximum short circuit current of 8.4 kiloampere. And also the same idea for this busbar that has a maximum short circuit current of 9.3 kiloampere. Alright. Also we have an important note here, which is that you can see when going down the short circuit current decreases and it doesn't increase. And this is because when going down the impedance of the circuit increases, and when the impedance of the circuit increases when going down, the short circuit current will decrease, as the impedance is inversely proportional with the current. So when the impedance increases, the current decreases. And for that reason, we will find that we have the maximum short circuit current at this position to be 11.2 kiloampere here at the secondary side of the transformer or at the terminals of the transformer, while at the last load we will find that the short circuit current is 8.4 kiloampere, which is smaller than this 11.2 kiloampere. Alright. Also, we can get the report of this network, or we can get the short circuit report that has all of the data we need about the short circuit calculations. And to get the short circuit report, we can press on this report manager, and then it asks us for the format of the report we need. So let's select the PDF mode, and then we specify the report we need. And here this is the path at which the report will be saved. So we can copy it and press OK. And after that, we can find the report as generating now. Alright, you can see this is the report we have for the short circuit analysis. Here we can go down to access the different parameters of this report. So those are the input data we have, and this is the data for the winding transformer or the distribution transformer. Those are the data that we have entered. And when going down, we will find that we have the rest of the parameters for the data that we have entered. So that's for the short circuit calculation and its report. Also, we can do the same thing for the load flow calculation or for the voltage drop calculations. Here we can go to the edit mode, and then we go to the load flow calculations, and then we run the load flow calculations. And after that, we can access the report of the load flow calculations. And here we select it to be a PDF report, and then we select it, and then we press on OK. So the load flow calculation report has been generated and it's opened automatically. You can see its name is the load flow analysis. And here when going down, we will find that those are the different data that we have entered of the network. And we will find that we have the voltage drop calculations down here, and so on. So you can analyze your report and you can use it to analyze the different parameters we have for the load flow calculations or for the short circuit calculations. Alright, so that's about this tutorial at which we have learned how to run the short circuit and the voltage drop calculations using the ETAP software. That's the clip right now. Thank you for watching and see you next tutorials.
Hello and welcome everyone. We're happy that we're all together again. In this tutorial, we will start talking about a new important topic, which is the power factor correction. So fasten your belt and let's get started. The aim of this tutorial is to know what is the idea behind the power factor correction, or why we need to perform the power factor correction in the distribution networks. And then we will discuss the different benefits of the power factor correction, as we need to know why we are using the power factor correction or what are the gains caused by the power factor correction. So let's go ahead. First of all, we need to revise the different kinds of the power that we are handling in the electrical power system, which we discussed before. Here we can revise with each other on this power triangle, which consists of the complex power or the apparent power as the hypotenuse of the triangle. And also we have the real power, which is represented as the base side of the triangle. And finally we have the reactive power Q, which is represented by the front side of the right triangle. So this is for the different kinds of power which are represented by the different sides of the triangle. Now for the important angle in this triangle, it's this angle here, which is the power factor angle phi, and you can see it lays always in front of the reactive power side. Very good. Now if we need to revise the definition of each type of those powers, we say that the active power P is the real power that the electrical loads are getting the actual benefit from. So the active power is a power that is converted to another type of energy that the electrical loads are consuming and getting the benefit from. And its unit is watt. So we measure the active power P in watt or in kilowatt. And we get the relation between the active power P and the apparent power S. To P this relation, here the active power P equals the complex power S times cosine phi, or times the power factor. And this power factor equals cosine the power angle, or cosine phi. So that's for the active power. And this power factor equals cosine phi, or cosine the angle of the power factor. So that's for the active power P. Now the second type of the power we have is the reactive power Q. And it's an amount of power that is absorbed by the load, but it's not a useful kind of power, or it's not converted to another type of energy that the electrical loads are getting the benefit from. So we say that the reactive power is a non-useful kind of power, and we don't need to increase it, but we need to reduce it as much as possible. But on the other hand, the reactive power has a useful effect on the electrical motors in conserving the stability of the electromagnetic field inside the motors. So the reactive power P is not useful on the electrical load, or it's not converted to another type of energy that the loads are getting the benefit from, but it has only one benefit, which is that it maintains the stability of the electromagnetic field inside the windings of the motors. And for its relation with the apparent power S, we find that it equals the apparent power F times sine phi, or times sine the power factor angle. Alright, now for the total power that the load is consuming, it's the complex power, or the apparent power, and it's a combination of the active power and the reactive power, and for that reason it's called the apparent power, as it's the power that appears totally that the load is consuming. And here it equals the square root of the active power P squared plus the reactive power Q squared. Hence, we say that the apparent power depends on both the active power and the reactive power, and once any of them increases, the total apparent power will increase. Very good. Now we can express the relation between those three kinds of power on another approximate way. Here, if the total complex power S is 100%, and we have a power factor of the electrical load of 0.8, at that case the active power P will equal a percentage of the total power complex S, so it will equal cosine phi times S, but cosine phi equals 0.8, so the active power P will equal 80% of the total power S. And also at that case we can consider the reactive power Q to be equal 20% of the total power. So we can consider that we are getting the benefit from just 80% of the total power, while 20% of the power is lost in a form of the reactive power Q. But as we said, we get the benefit from the active power P, and we don't get the benefit from the reactive power Q, so we need to decrease the reactive power Q as much as possible to increase the active power P as much as possible, as we are getting the benefit from P, not Q. And to solve this problem, we need to increase the power factor of the electrical load, as when the power factor increases, the total active power will increase, as the active power is directly proportional to the power factor. So suppose we increase the power factor to P equal 0.9 instead of 0.8. Here at that case the active power P will equal the power factor times S, so it equals 0.9 times S, which means that we have now an active power of 90% of the total apparent power S, while the reactive power Q will be equal only 10% of the total power we have. So by that way we reduce the reactive power Q and we increase the total active power P at the same time. And this is by increasing the power factor cosine phi, or in other words, we are improving it. And this is what's called the power factor correction, as the power factor correction is the case at which we increase the power factor of the electrical load to increase the useful power P and decrease the unuseful power Q as much as possible. Alright, but now you can ask, why we need to increase the power factor of the electrical load, or what are the benefits of the power factor correction?
Here we say that the power factor correction has some great benefits on the electrical load that we are aiming to have or that we are aiming to achieve. And the first benefit of the power factor correction is to reduce the total consumed apparent power, which leads to an economical benefit as we are reducing the cost because we are reducing the total consumed power. So suppose we have this power factor triangle that has a total reactive power of Q1. Now suppose we decrease the power factor angle, which leads to an increase of the power factor of the electrical load. And at the same time, the total consumed reactive power now will be reduced from Q1 to Q2. Here at that case, the total consumed apparent power will be reduced also from S1 to S2. As you see, S2 is less than S1. So we have consumed a total apparent power now S2, which is less than the old apparent power S1. And by the same way, the power factor angle has been decreased much more to have a larger power factor. At that case, the total consumed reactive power Q now will equal Q3, which is less than Q2. And at the same time, the total consumed apparent power will be S3, which is less than S2, which is less than S1. So we can conclude that by increasing the power factor of the electrical load, we are decreasing the total consumed reactive power, and at the same time we are reducing the total consumed apparent power, and as a final result we are decreasing the economical cost of the consumed power by decreasing the total consumed power. So we are getting an economical benefit at that case, as the cost now is less than the cost at the second case, and it's less than the cost of the first case. Very good. Also, the second benefit of the power factor correction is that we are decreasing the total consumed current of the electrical load, and this is because the apparent power P equals the current absorbed by the load times the load voltage. So when increasing the load power factor, the total apparent power will decrease. Hence, the total absorbed current will decrease as the current is directly proportional to the apparent power. But this decrease in the electrical current will result in reducing the cross-sectional area of the cables, as the cross-sectional area is directly proportional with the current absorbed. So, by that way we get an economical gain, as when the current decreases, the cable cross-sectional area will decrease. Alright. Also, the third benefit of the power factor correction is to get smaller power losses in the system we have, as the power losses equals the current square times the resistance of the electrical load. But as we said before, the power factor correction results in less current losses, which results in less power losses. So we are saving much power at that case. And by the same way, the power factor correction results in less voltage drop, as the voltage drop equals the current times the resistance. So when the current decreases due to the power factor correction, the voltage drop will decrease by the same way. So we are getting a higher voltage value at the end of the electrical load, and we are getting a more strong power system at that case. And now the final benefit of the power factor correction is to increase the efficiency and the lifetime of the electrical load. And this is because when the electrical current increases, the heat produced through the electrical load will increase. And when the heat increases, this will reduce in a lower lifespan of the electrical load, and it will result in a lower efficiency also of the electrical load. So we decrease the load current to decrease the heat produced by the load, hence we increase the lifespan and the efficiency of the electrical load. More than great. So that's about this tutorial at which we discussed the idea behind the power factor correction, and we knew the different benefits of the power factor correction. Hope that's it right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In this tutorial we will continue talking about our new important topic, which is the power factor correction. So fasten your belt and let's get started. The aim of this tutorial is to discuss the different designing steps of the power factor correction. So we need to know how the power factor correction system is constructed. So let's go ahead. First of all, the first step of the power factor correction is to specify the old power factor or cosine phi 1 that we need to correct. So we have the old power factor of the electrical load that we need to correct, and we set this old power factor to be a standard value of 0.8. And then we specify the new power factor or cosine phi 2. And this new power factor is the corrected power factor or the improved power factor that will get a correct design of the total reduced apparent power. And we set this new power factor to be a value of about 0.95, and this is also a standard designing value. So if the active power of the electrical load is a constant value P, and for the old complex power it has a standard value of S1, and for the old power factor its value is cosine phi 1, or for the old power factor angle its value is phi 1, and also for the old reactive power value its value is Q1, and for the new complex power value its value is S2, which is the reduced complex power. And we have also the new power factor angle, which is phi 2, which is the reduced angle. And this reduced angle will result in a reduced reactive power value of Q2. Here at that case, our aim is to move from this larger rectangle to this reduced rectangle, which has the corrected power factor. Very good. Now our third step to do after specifying the old and the new power factor values is to specify the element that will be used to correct this power factor. And for the element that is used to correct the power factor, they are some capacitors that are connected together to perform or to form a capacitor bank. So it's called a capacitor bank because it's a collection or some capacitors that are accumulated together to improve the power factor of the electrical load. But you can ask now, what are the causes that cause the power factor of the electrical load to be a PAD 1 or a lower power factor? Here we say that for the electrical loads that are having some windings or some coils that causes the power factor to be a PAD 1. This is because the coils are making the power factor angle to be a larger one, which result in a lower power factor, which results in a higher reactive power value. So we use the capacitor bank to reduce the effect of the winding or the coils, as the capacitor bank reduces the power factor angle, which results in a larger power factor, which results finally on having a smaller reactive power consumed or a smaller Q value. So we can say that we compensate the difference between the old reactive power value Q1 and the new reactive power value, which is Q2, by the reactive power QC, which is the reactive power produced by the capacitor bank. So we can reform the relation between the three parameters Q1, Q2, and QC in this equation, where QC equals Q1 minus Q2. But as Q1 equals the active power P times tan phi 1 and Q2 equals the active power P times tan phi 2, so we can get the value of the capacitor bank from this equation. As all of the parameters of this equation are given, here P is the electrical load active power and phi 1 is the old power factor angle, and it equals cosine minus 1 0.8, as 0.8 is the old power factor, while phi 2 is the new power factor angle, and it equals cosine minus 1 0.95, as 0.95 is the new power factor. So by that way we can detect or specify the capacity of the capacitor bank in kilovar or in kilovolt ampere reactive. And this is by knowing the old power factor and the new power factor and the active power of the electrical loads. Very good. Now the fourth step after detecting the kilovar of the capacitor bank is to specify the number of the variable steps that the capacitor bank will be divided into. And those variable steps means that not all the amount of the capacitor bank will be connected to the electrical loads at the same time, but this QC will be divided into some steps, and those steps are entering the circuit one by one. But the important question now is that, why we need to divide those capacitors into some steps? Or what's the benefit of dividing the capacitor bank into some variable steps? Here we can take this example. Suppose we have this transformer which is rated 500 kilovolt ampere, for example, and this transformer is feeding those three different sub-main distribution panels, and the power of each panel of those three distribution panels is 150 kilovolt ampere, 150 kilovolt ampere, and finally 100 kilovolt ampere respectively. Now if we need to get the value of the capacitor bank in kilovolt ampere reactive or in kilovar, it will equal the total active power P, which equals the transformer rating of 500 kilovolt ampere times 10 the old power factor angle, which is 36.8, minus 10 the new power factor angle, which is 18.1. So at that case we will get a total reactive power value of 210.6 kilovar or kilovolt ampere, and it will be connected to the main distribution panel directly. This is in case of all of the electrical loads on all of the sub-main distribution panels are working at the same time with no problem, or in other words, the transformer is working with its full load. This is because the QC value is designed on the full load of the transformer of 500 kilovolt ampere. So we say that if we have just one fixed step QC, and all of the three panels are loaded with their full load at the same time, there will be no problem at the system, or the system will be working smoothly. But actually what happens is that the distribution network is not usually loaded with its full load, as in some cases we may find the first sub-main distribution panel to be loaded, for example, with a value of 100 kilovolt ampere instead of its full load of 150 kilovolt ampere, and the second distribution panel may be loaded with just 50 kilovolt ampere instead of 150 kilovolt ampere, and the same thing for the third distribution panel, as it may be loaded with only 50 kilovolt ampere instead of its full load of 100 kilovolt ampere. So we find that the total active power to be decreased, but the problem now is that the capacitor bank is still supplying a reactive power of 210 kilovolt ampere reactive, as it's connected as one step. And at that case, although the active power P has been decreased, the reactive power Q is still constant to be 210 kilovolt ampere reactive. So this means that at that case we are having a larger value of the reactive power QC than the required value. And we can find the relation of the QC and the voltage to P, QC equal the voltage square over XC, or over the reactance, and at that case the reactive power QC has been increased, so the voltage level will increase through the network, and this will result in a great increase or a great damage of the electrical load, as the electrical loads are working on a fixed voltage value or the nominal voltage value, but the voltage at that case has been increased greatly, so the electrical loads may be damaged or it may be broken. And for that purpose, we come up with the idea of the variable steps of the capacitor bank, as according to the percentage of the active power that is actually absorbed by the electrical load, we are adding the required amount of the reactive power QC to be connected to the network. Or in other words, not all of the amount of the reactive power is connected to the network at one time, but we are dividing the total amount of the reactive power into some steps. For example, this 210 kilovolt ampere of the capacitor bank is divided into 3 steps, or it may be divided into 3 steps, and each of them has a reactive power value of 70 kilovolt ampere reactive. And also each step of them will be controlled according to the absorbed value of the active power of the load. For example, if the transformer is at the no load state, so it will be loaded with 0%, and at that case the 3 steps will be off or they will be disconnected. But suppose another case at which the transformer is loaded with 30%, here at that case just one step will be on while the 2 other steps will be off. And also we have the third step at which the transformer is loaded with 60% of its full load, and at that case 2 steps will be on at the same time while the third step will be off. And finally, the final step we have, or the final case we have, is the case at which the transformer is loaded with 90% of its full load, which means that 90% or more of the total active power are on at the same time, and here at that case the 3 steps will be on at the same time. So this is the idea behind the variable steps of the transformer, which is to divide the reactive power into some steps which is getting online to be connected to the network according to the percentage of the active power loading. More than great. So that's about this tutorial at which we started talking about the different implementing steps of the power factor correction. Hope that's clear right now. Thank you for watching and see you next tutorial. Hello and welcome everyone. We're happy that we're all together again. In this tutorial we will continue talking about our important topic, the power factor correction. So fasten your belt and let's get started. The aim of this tutorial is to continue discussing the different steps of designing the power factor correction system. So we need to know how can we construct an accurate power factor correction system. So let's go ahead. Now we need to know what are the steps of the capacitor reactive power that we can find in the market. Here we find that we have some different power ranges or some different standard power ranges that are available in the market which we can select from. And those standard values of the capacitors are 12.5 kV, 20 kV, 25 kV, 30 kV, 40 kV, 50 kV, 60 and finally 75 kVA. So those are the standard ranges that we can find and buy from the market. But there will be a fixed step that is connected to the circuit anyway, regardless to the value of the variable steps. And this reactive power value of the fixed step depends on the power rating of the transformer itself. As if the transformer power rating is less than 2 MVA, the fixed step of the capacitor bank at that case will be 50 kV, and an example on that, if the calculated total required reactive power is 200 kVA, here at that case we can divide the number of steps into 4 steps. One of them will be a fixed step of 50 kV and another 3 variable steps, and each of them will be rated of 50 kV. So this is in case of the total power rating is less than 2 MVA. But in case of the power rating of the transformer is larger than 2 MVA, at that case the fixed step will be 75 kV and the rest of the steps will be some variable steps. For example, if the total required QC value is 375 kV and we decided that we will use 6 steps, at that case the number of steps will be a fixed step of 75 kV and another 5 variable steps, and each of them is rated 75 kV. So it will be 75 plus 5 times 50 kV. Alright, now after specifying the number of steps, we have the next step, which is to specify the voltage range of the capacitor bank. As for the 50 Hz voltage system, the voltage level will be 400 volts for the line voltage. But if we open the datasheet of the capacitor bank, we will find that the capacitor bank is designed to withstand a higher level of the voltage, which is larger than 400 kV, although it will work actually on a nominal voltage of 400 volts. And the reason of designing the capacitor bank on a larger range of voltage that is larger than 400 volts is that when the capacitor is getting on or off, the network will have a very large charging current, which is called the surge current. and this surge current makes the voltage level across the capacitor to increase. So for the capacitor bank to withstand this instantaneous increase in the voltage and the current, it's designed with a higher level of voltage that is higher than 400 volts. Very good. Now the next step of the power factor correction system is to specify the connection of the capacitor bank. And the first type of the connection of the capacitor bank is the star connection, but it's a less common used method. While for the most common used method it's the delta connection, and this is the configuration of the capacitor bank inside the capacitor itself. So we get the three terminals finally out of the capacitor bank, which represents those three terminals as you see, as the capacitor bank is connected to the three-phase through those three terminals. But this delta connection of the capacitor bank is the most common used method due to its economical benefits, as it's more economical than the star connection, and also it reduces the harmonics and the distortion of the voltage sine wave. So for the harmonic effect on the voltage sine wave, which produces some distortion of the sine wave itself, here we use this delta connection of the capacitor bank to reduce the third harmonic of the voltage sine wave. Alright, now the final step we have in the power factor correction steps is to design the different parameters related to the capacitor bank, as the capacitor bank is connected to a three-phase supplying source across a circuit breaker. And here there are some cables that are connected to the capacitor bank and the circuit breaker. So we need to know how to design the different parameters of the circuit breaker and those cables connected to it. Now the first parameter we calculate is the rated current passing through the capacitor bank. And because it's a three-phase load, so its rated current equals 1.5 times the kilovolt ampere of the capacitor bank. And then for the circuit breaker current, it equals a safety factor times the rated current. And this safety factor equals the overloading factor, which equals 1.5. And this overloading factor results from the overloading condition that may occur through the capacitor bank. And then the second safety factor multiplied by it is 1.3, which is the surge current factor. And this is, as we said before, because there is a large surge current passing through the capacitor bank as a result of the starting and the ending of the capacitor bank. So by that way we detect the circuit breaker current. After that we select the next standard of the circuit breaker, which is the next larger standard value of the circuit breaker in ampere, which we can find in the market. And after that we detect the cable that is connected to the capacitor bank, and we find this cable current to be equal the circuit breaker rating over the derating factor of 0.8. And from here we can detect the cable cross-sectional area from the catalog or the data sheet of the manufacturing company of the cable. And this is according to the cable current, exactly as what we did in the cables design before. More than great. So that's about finishing the different steps of the power factor correction system. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In this tutorial we will start talking about the designing process of the different components in the low voltage distribution system. So fasten your belt and let's get started. The aim of this tutorial is to learn about the designing process of the distribution system for the different components in the low voltage distribution system. So we need to know what are those different components and how can we select them. So let's go ahead. First of all, if we need to express the first element in the distribution system, we find it to be the medium voltage load break switch, which is used for feeding the distribution transformer from its medium voltage side. And then the transformer steps the voltage down to the low voltage level and the low voltage side of about 40 volts. This is for the 50 Hz system. And the outgoing of the transformer is going to the main distribution panel. And as we learned before, the main distribution panel consists of some circuit breakers, one ingoing circuit breaker, and some outgoing circuit breakers. After that, we find those outgoing circuit breakers of the main distribution panel to be connected to some distribution elements, which is called the feeder pillars. And those feeders pillar is used to make a junction between the main distribution panel and the electrical loads that those panels are feeding. As this feeder pillar consists of a number of three-phase fuses, and each three-phase fuse is called a line. And the number of lines equals the number of electrical loads that this feeder pillar will feed the power to. For example, when I say a 7-line feeder pillar, this means that this feeder has 7 three-phase fuses, and each three-phase fuse of those 7 fuses will go directly to feed a specific load, and so on. And then after the feeder pillar, we have another element which is called the coffret. And this coffret is a three-phase fuse that is used to feed the power directly to the electrical load. So it's a single-phase, three-phase fuse, and it's used as an input for the electrical load. For example, suppose we are having a 2-line feeder pillar. At that case, each pillar will feed 2 coffrets, and each coffret will feed a specific building, as the coffret is the input of the building. And this coffret is considered to be a three-phase fuse that is used for protecting or breaking the circuit in case of the current passing through it is larger than the rated current. Very good. Now let's talk in some details about each of those elements in the distribution network. As we said, the first low voltage element we have is the distribution transformer, and this distribution transformer has 2 types. The first one is called the oil transformer, and here this is the shape of the oil transformer. And for the oil transformer, it uses the oil for the ventilation and the isolation process, as the oil lays inside the transformer tank that has the 3-phase windings. So this oil ventilates the phases, or it decreases the heat that is dissipated from the phases windings due to the current that passes through the different phases. And also the oil isolates the different phases from each other, so it's used for the isolation process. Very good. Now the second property of the oil transformer is that it needs larger maintenance. So the oil transformer needs maintenance frequently due to its construction to have an oil inside it. And also for the oil transformer, it's loaded on about 80% of its maximum loading capacity. And this is because the oil transformer produces its maximum efficiency when it's loaded on just 80% of its maximum power. While if we loaded the oil transformer on 100% of its rated power, it will produce larger losses. Hence, if we are having an oil transformer which is rated, for example, of about 1000 kilovolt ampere, it will be loaded with a maximum power rating of 800 kilovolt ampere. This is to produce the best results or to reduce the losses as much as possible. Also, the next property of the oil transformer is that it has a larger size, and this is compared to the dry transformer type, as the dry transformer has a smaller size. And also it has larger losses, as we said, so the losses on its power is larger. This is for the oil transformer type. And due to those disadvantages of the oil transformer type, we find its cost to be less. So if we put an oil transformer, it will cost us less money. Very good. Now the second type of the transformers we have is the dry type transformer. And this is the shape of the dry type transformer. And it's called dry because it has no oil inside it, or it uses the air for the ventilation and the isolation process. Hence, we can note here that the dry type transformer has some fans like those ones, and those fans are used for the ventilation purposes. So the air now is used for the ventilation and the isolation purposes for the different phases of the dry type transformer. But the advantage of the dry type transformer is that it needs less maintenance, And this is because the electrical faults that occurs on the dry type transformer is less, hence we don't need to maintain it frequently. And this is also because it's a dry type, not an oil type, as the oil type needs larger maintenance compared to the dry type transformer. And also the next advantage of the dry type transformer is that it can be loaded on 100% of its full load. As this type of transformer has smaller losses in the power, so it gives its maximum efficiency when it's loaded on 100% of its full load. Also, its next property is that it has a smaller size, and this is because it has no oil inside it, as the oil takes a larger area, and here as we have no oil, so we are having a smaller area for the dry type transformer. And also, as we said, for the dry type transformer, its losses is less, hence we get the larger efficiency of the dry type transformer. But for those advantages of the dry type transformer, we find its cost to be much. So its price is larger compared to the oil type transformer. Alright. Now if we need to know what are the power ranges of the distribution transformers that we can find on the market, we can say that we have those ranges of the power to be 100 kilovolt ampere, 300 kilovolt ampere, 400, 500, 630 kilovolt ampere, 800 kilovolt ampere, and then 1000 kilovolt ampere, and 1250 kilovolt ampere. After that we have 1500 kilovolt ampere, then 1600 kilovolt ampere, and 2000 kilovolt ampere, 2500, 30,000, 4,000, and finally 5,000 kilovolt ampere. So those are the different power ranges of the distribution transformers that we can select from them in the market. Hence, we can select of those ranges according to the total power that we need. Very good. Now the second component we have after the transformer is the main distribution panel. And as we said, the main distribution panel is a panel like that one that has three-phase ingoing circuit breaker, which may be an air circuit breaker like that one here. And this circuit breaker is connected directly to the transformer output as an ingoing circuit breaker. And then we are having the outgoing circuit breakers like those ones. And for each outgoing circuit breakers of those circuit breakers, it may feed an electrical load directly, or it may feed the electrical load through the feeder pillar. Hence, we find the next element to have is the feeder pillar. And this feeder pillar, as we said, consists of some three-phase fuses, which forms three-phase circuits like those ones here. And each circuit of them will go directly to feed a specific building or a specific load. For example, this is a 7-circuit pillar, which means it consists of 7 circuits, and each circuit of them has 3-phase fuses, 1 fuse for each phase. And also each circuit of them will go directly to feed a building that has a link between it and the pillar, and this link is the cover, as we said. This is because we are not entering the building directly to feed it, but we are having a link between the building and the pillar, which is the cover. And this cover, as we said, is just a 3-phase circuit that has one line, which consists of a 3-phase fuse like that one here. And as we said, it takes its input from the feeder pillar and it feeds the building with the electrical power directly. And we use those fuses inside the cover panel to protect the circuit from the overloading current or from the short circuit current. So the fuses are used in that case as a protection element. Hence, we can conclude that we use the cover as an input for each building, as it's responsible for feeding a specific building, as each building is having a specific cover to feed it. Very good. After that, if we are entering the building, we will find that we are having the main distribution panel, which consists of an ingoing circuit breaker and some outgoing circuit breakers. And those outgoing circuit breakers are going to feed the sub-main distribution panels and the different floors of the building. as each floor will have a specific sub-main distribution panel inside it. For example, the main distribution panel lays in the ground floor, as each of those sub-main distribution panels lays on each floor. So we have the first floor sub-main distribution panel lays on the first floor to feed the loads which lays on the first floor, and we are having also the second sub-main distribution panel which lays on the second floor to feed the loads that lays on the second floor, and by the same way we are having the third sub-main distribution panel which is used for feeding the electrical loads that lays on the third floor. And if we focus on one sub-main distribution panel to analyze it, we can find that it has an ingoing circuit breaker and it has some outgoing circuit breakers. And each of those outgoing circuit breakers are used to feed some other distribution panels. So in the first floor, we will find that it has 3 outgoing sub-main distribution panels. Here, the socket sub-main distribution panel, and the lighting sub-main distribution panel, and the air conditioning sub-main distribution panel. So we use the first floor sub-main distribution panel to feed those 3 sub-main distribution panels in the first floor. Here one for the lighting, one for the sockets, and finally one for the air conditioning electrical loads. And also the same idea is applied on the second floor and on the third floor, as we will find that their sub-main distribution panels are feeding some other panels, which are the lighting panels, the socket panels, and the air conditioning panels. More than great. So that's about this tutorial, at which we learned about the different components that lays in the distribution network. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In this tutorial, we will start talking about a new important topic, which is the electrical panels balancing. So fasten your belt and let's get started. The aim of this tutorial is to know how to design a correct electrical distribution panel design, which achieves the required system balancing, or which avoid the unbalancing condition. So let's go ahead. First of all, we need to know what is the idea behind the distribution panels balancing, or why we need to design a balanced electrical distribution system when we are making our panels design. Here we say that, suppose we have those 3 phases, phase R, S, and T. At the ideal case, the current passing through the phase R equals the current passing through the phase S equals the current passing through the phase T. And this is the balanced condition, at which each phase is carrying an equal power of 100%. For example, phase R is carrying 5 amperes, phase S is carrying 5 amperes, and phase T is carrying the same 5 amperes. So this is the ideal case with no problem, and the distribution system will work smoothly with no problem, as each phase is designed to carry those 5 amperes with no problem. And this is what's called the balancing condition. But suppose now the system has been changed to have the phase T carrying just 60% of the full load, and phase S is carrying 70% of its full load. Here, at that case, the problem will appear in the phase R, as it will carry the rest of the total power of 170% of the total power. And this means that it's carrying now its full load of 100% plus the rest of the power from the 2 phases, which are 30% plus 40%. So at that case, the phase R is loaded with an extra load of 70%. And the problem lays in that each of those phases is designed to be loaded with a maximum power of 100%, but when we add an extra load of 70% at any phase, this will result on an overloading condition on that phase, and this phase conductor may be damaged or burned out due to the extra current that we are forcing to pass through this phase. And this is what's called the unbalancing condition. So our aim now is to avoid this unbalancing condition, or to avoid the overloading condition of one phase, as this will cause the phases to be damaged or burned out. And for that purpose, we designed the distribution system to have each phase to be carrying the same current or the result of the phases to be balanced. As our ideal case is to have phase R carrying the same power of 100% and phase S is carrying the same power of 100% and the same thing for phase T to be carrying 100%. Very good. Now we can apply this concept on the distribution panel's design. Suppose we are having a three-phase lighting panel which has the three-phase ingoing circuit breaker and it has 12 single-phase outgoing circuit breakers, and each of them is connected to a specific lighting circuit that has a specific power. So those 12 single-phase circuits are connected to the different phases, the phase R, the phase S, and the phase T. And suppose those are the power values for each circuit of the 12 circuits. Here the first circuit has 100 volt ampere, the second circuit 200 volt ampere, the third circuit 150, the fourth circuit 300 volt ampere, and so on until the final circuit we have. Now we can analyze this distribution panel much more to see the total power of each phase of the three phases by knowing the number of circuits connected to each phase and the total power of those circuits connected to each phase. Here, suppose those are the three phases R, S, and T, and this is the ingoing three-phase circuit breaker. And now for the phase R, it's having a circuit for 300 volt ampere, and another circuit of 100 volt ampere, and a third circuit of 100 volt ampere, and finally a fourth circuit of 100 volt ampere. So if we calculated the sum of the total power through the phase R, it will be 300 plus 100 plus 100 plus 100, which equals 600 volt ampere. And then for the second phase S, it has another fourth circuit connected to it, and the power of those circuits are 150 volt ampere, 150 volt ampere, 300 volt ampere, and finally 150 volt ampere. So the sum of those four circuits is 750 volt ampere. And finally, the third phase T is having those four circuits connected to it, which are having a power of 200 volt ampere, 100 volt ampere, 150, and finally 150 volt ampere. So we find the total power connected to the phase T to be 600 volt ampere. And as a result, we note that the three phases R, S, and T are carrying the different power values which are different from each other. As the first phase is carrying 600 volt ampere, the second phase is carrying 750 volt ampere, and the third phase is carrying 600 volt ampere. Hence, it's very obvious that we are at an unbalancing condition at that case, as the three phases are carrying different current values from each other. And if we need to check the unbalancing percentage, we can get the total power of the three phases and divide them over 3 to get the equal power percentage at the balancing case. But the total power of the three phases are 600 plus 750 plus 600, which equals 1950 volt ampere. Hence we divide 1950 over 3, which gives us 650 volt ampere. So we can get the first phase power percentage to be 600 over 650, which equals 92%. And for the second phase percentage, it equals 750 over 650, which equals 115%. And for the third phase, its power percentage equals 600 over 650, which gives us 92%. So we can conclude now that this is a wrong design because it has an unbalancing distribution system, as the first and the third phase are unloaded with 9%, while the second phase is overloaded with 15% over than its normal loading condition. So those 15% overloading may damage the second phase or it may be heated. And for that reason, we should make a distribution panel design which approaches the balancing condition as much as possible, as the ideal case with the balancing condition should have each phases to be loaded with 100%, so we should have an equal loading condition of each of the three phases. Hence, we need to have the first phase and the second phase and the third phase to have a power value of 650 volt ampere. But for the actual design, we may not have the three phases to carry an equal power sharply. So the standard design in the code says that the accepted unbalancing percentage must be less than 10%. So we can have an unbalancing percentage up to 10%, which is the accepted value. While if the unbalancing percentage becomes larger than 10%, we should modify the design at that case to replace some loads from some phases and add them to other phases, and this is to maintain the unbalancing percentage to be less than 10% for the correct distribution power design. And we can calculate the unbalancing percentage by calculating the average power of the three phases firstly, as the average power equals the sum of the three phases power over 3. So it equals S sub R plus S sub S plus S sub T over 3. And by that way we are getting the ideal power value of each phase, or that each phase should carry at the balancing condition or at the ideal balancing condition. And then we get the maximum unbalancing power value to be equal to the power of the largest phase minus the power of the lowest phase, so it equals S maximum minus S minimum. And then we get the unbalancing percentage to be equal the maximum power of the maximum phase minus the minimum power of the minimum phase over the average power times 100. So by that way we can get the unbalancing percentage, and this percentage must be less than 10% for a correct distribution panel design. Hence, we adjust the arrangement of the different circuits to have finally a total unbalancing condition which is less than 10%. More than great. So that's about this tutorial at which we learned how to make a correct balanced distribution power system. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we are all together again. In this tutorial we will learn with each other how to design the balancing system for the electrical load distribution panel practically using the Excel software. So we need to design an Excel sheet that is capable of designing the load balancing of the distribution panel in an automatic way without the need of making the calculation manually each time. So once we enter the data to the program, it will be able to make the balancing calculations, and we will be able to adjust the design quickly to reduce the unbalancing percentage to get an accurate balancing system of the distribution panel. So let's start. First of all, we need to design the balancing system for the same lighting distribution panel that we have explained on the previous tutorial. And to work on the same distribution panel that we have designed, we can paste its picture here. So we press on insert and then picture, and then we can select this is the picture of the distribution panel we have, and then we insert it at this position. Very good. Now if you remember, this distribution panel consists of a 3-phase ingoing circuit breaker and a number of outgoing circuit breakers, and each of those outgoing circuit breakers is connected to a lighting circuit, and we need to express the power that will be connected to each of those circuits for the 3 phases R, S, and T, as we will attach each group of circuits to a specific phase of the 3 phases. So let's select a specific column, for example to be this column, and we will specify it to be the column for the phase R, and we will add the circuits of the phase R to this column. Here we type on the first cell R to represent it to be the phase R, and then we can increase its font size to be 24. After that we can fill the cell color to be orange one, and we can change its font color to be white. Also we can change the font to be Century Gothic. That's it. Then we can center it. And then we need to set those pillow soles with the same format of this sole. So we can select this sole and press on Format Painter and select those down soles. Alright. Also we can decrease the pillow soles font color to P24. So let's select them and then make their font size to P only 16. That's it. Also we need to select the format of this sole. Here we select it and select its format and give the second column the same format. Here we go down. But as we will use this column for the phase S, so we will change its color to P a blue one. Here we select its color to P blue and then we specify the format of this column also and give it to this column. But as we will use this column for the third phase, which is T, so we will change its color to P, the red one. And then we select this phase to PS and this third one to PT. Very good. So those are the three phases, R, S, and T. Also we can select all of those soles and change their border style to P, this one. Very good. Now what we will do is to distribute the circuits on the different phases of the three phases. So we can select this distribution panel and make it up here. Now for the first phase R, we will add the first circuit to it. So let's specify the 150 volt ampere to the phase R. Here we type 150. Then for the phase S, we will select also the circuit which has 150 volt ampere. So we select here 150 volt ampere. After that, for the phase T, we will pick the first circuit to P, this one which has a volt ampere value of 300. So we will set this one to P 300 volt ampere. After that, we start pack with the first phase R. So we will pick this 150 volt ampere circuit to it. Here we type 150. Then for the second phase S, we will pick this circuit to add it to the phase S. So the circuit has a power value of 300 volt ampere. Here we type 300 volt ampere. And after that, for the phase T, we will select this 100 volt ampere circuit to it. So we select here 100 volt ampere. That's it. Then we start pack with the phase R. Here we will pick the circuit which has a power value of 100 volt ampere. So we type here 100. Then for the phase S, we will select this power value or this circuit that has a power value of 150 volt ampere. So we select 150. After that, for the phase T, here we will select the circuit that has a power value of 100 volt ampere. So we type 100 and then we jump back to the first phase. So for the first phase, we will select the circuit that has a power value of 200 volt ampere. Here we type 200, and then for the phase S, we will select this circuit here that has a power value of 150 volt ampere. Here we type 150, and finally we have the final phase T, and for that we will select the circuit that has a power value of 300 volt ampere. So what we have done now is to add each group of circuits on one phase. So we have finally 4 circuits for the phase R, and 4 circuits for the phase S, and finally 4 circuits for the phase T. And now what we need to do is to get the sum of the total power connected to each phase of those 3 phases. So let's zoom out a little bit. Then we select this cell and type here sum. And then we can give it the same format of this cell. Here we press on Format Painter and select this one. Also we can increase the width of this cell a little bit. And here we can change its fill color to P a grade one. Also we can increase its font size to P26. And here at this cell we will add all the power values that are connected to the phase R. So we type here equal and then sum and open a parentheses and select the cells starting from this one and we drag down to the last cell and then we close the parentheses and then press enter. Very good. So you can see the power or the total power connected to the phase R is 600 volt ampere. But for simplification, let's delete those rows. Here we don't need them. We press right click and then delete. Then we need to do the same thing for this second phase. Here we access the cell and press equal and then use the sum function to sum all of the power of all of the circuits connected to the phase S. Here we start from this cell and we drag down until the last cell and close the parentheses and press enter. Very good. So the total power connected to the phase S is 750 volt ampere. And finally, for the phase T, we press equal and then sum, and we start from the first cell and we drag down to the last cell and close the parentheses and press enter. Very good. So you can see the total power connected to the phase T is 800 volt ampere. Now, after getting the total power connected to each of the three phases, we need to get the unbalanced percentage to know if it's an accepted value or not. And for that purpose, we will select this cell and paint its format and give it to this cell. Then we can change just the color or the filling color of this cell to be this purple one, for example. And then we can increase the width of this column a little bit. And here we type the percentage of the unbalance. And then equal. And press enter. Now let's decrease the font size a little bit. Also, we can zoom in a little bit and go down. And for that purpose, to apply the unbalanced equation, here we access this cell and type equal. And then we need to apply the same equation that we have discussed on the previous tutorial. And if you remember, the unbalanced equation was equal the power of the maximum phase minus the power of the minimum phase over the average power value of the three phases. So to detect the maximum power of the maximum phase, we use the max function. So we type max, and then we open a parentheses, and we select the cell, and we drag. Here we drag to this cell. So this equation will detect automatically the maximum value of those three cells. And then we close the parentheses. Then we type minus, and then we need to detect the minimum power value of those three phases. So we type minimum, and then open a parentheses, and we select the same three cells. So we select this cell, and then we drag to the last cell, and then close the parentheses, and then we need the general parentheses for those two values. So we need to include the minimum minus the maximum on a general parentheses. So we select it. Very good. Now it will be over the average value. So to detect the average value, we easily open another parentheses and then use the average equation. So we type AV and E and R. Here this is the average equation. Then we will select those three values. So we select this cell, and also we drag to the last cell, and then close the parentheses, and then close the other parentheses, and then we type times 100. This is to detect the percentage of the unbalance and 100%. So we type 100 as we need the percentage value. After that, we press on enter. Very good. Here you can see the unbalanced value or the unbalanced percentage of those three phases are S and T. Here it's 27. Now let's zoom out a little bit. Then we need to get those three cells the same format of this cell. So we select this cell and press on Format Painter and select those three cells. And then we need to merge those three cells. So we select them. Then press on Merge and Center. Very good. So you can see the unbalanced percentage that we have got now is 27%, which is a very larger value. But as we learned it before, the maximum unbalanced percentage must be less than 10%. So it's obvious that we have got an unaccepted unbalanced percentage as it's larger than 10%. So to solve this problem, we need to adjust the distribution of the different circuits on the different phases. And for that, we can do a list modification to pick this 100 circuit from the phase T, for example, and we can add it to the phase R. So we can select the cell and delete its content, and we can add it to the phase R. Here we type 100. Very good. You can see the power values or the sum of the power values of the three phases has been changed. Here the sum is 700, and for the phase S it's 750, and for the phase T it's 700. And this is to give us finally an unbalanced value of 6.9, which is less than 10%. So this is an accepted value for the unbalanced percentage. And by that way, we managed to design a correct distribution balancing design, which achieves the balancing condition. So if you faced like those unbalancing condition, you just need to adjust your arrangement of the different circuits on the different phases to get finally a correct balanced panel design. And by that way we managed to design an automated program for calculating the unbalancing design for any distribution panel we have, and instead of trying the manual calculations, as you just need to fill this table with the power values of the three phases and it will detect for you the unbalancing percentage. More than great. So that's about this tutorial. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we are all together again. In this tutorial we will design with each other a single line diagram for a lighting distribution panel as an AutoCAD layout. So we need to know how can we draw a single line diagram for any distribution panel we have. And for that purpose we will design the single line diagram for the same distribution panel which we have designed its balancing system on the previous tutorial. So let's start. If you remember, for any distribution panel it consists of an ingoing circuit breaker and some outgoing circuit breakers. So we need to draw firstly the ingoing of this distribution panel, but as it's a lighting distribution panel that lays in the first floor, it will take its input from a sub-main distribution panel which lays in the first floor. So we need to indicate that this panel takes its input from a sub-main distribution panel which lays in the first floor. And for that purpose we will draw a line here. So we press on L and enter, and we will start from this point, and then we can activate the ortho mode to make a perpendicular line. Here we go until this point, and then we go down until this point, and then we press on escape. Hence, this line will represent the input of this distribution panel, or the input for the three-phase circuit breaker of this distribution panel. So this will be the cable that will be connected directly to the three-phase circuit breaker, which is the ingoing of the distribution panel. Hence, we need to attach this line with the circuit breaker, and for that purpose we have a ready plug for the circuit breaker that we can get from this legend here. So this is the distribution panel system legend, and here we have a three-phase circuit breaker. This is its sample here, so we can select it and then press C, O and enter. This is to copy it, and we can copy it from this point. So we will select this point as our paste point, and then we go there here until this point, and then we insert it at this position exactly. Very good. Now we press on escape. As you see, this is the three-phase cable, and we have connected it to the three-phase circuit breaker, or the three-pole circuit breaker, which is the ingoing of this distribution panel. After that, we need to go out of this circuit breaker with the connection that will be connected to the distribution panel. So we need another busbar, or we need another line that will be connected to the distribution panel as an outgoing of the circuit breaker. So this is the outgoing terminal of the circuit breaker. So we press on L and enter, and we start from this point, and we go until this point, and then we press on escape. So this is the outgoing for the circuit breaker which will be connected to the distribution panel. After that, we need to draw the main busbar of the distribution panel, which will represent the busbar of the three phases of this distribution panel. Hence, we can draw a rectangle that represents this busbar. So we press on R, E and C for drawing the rectangle, and then we press on enter, and here we start from this point, and we go until this point here. So this will be a suitable width for our busbar, and then we press a left click. Then we need to hatch this busbar, or to fill it with a solid color. So we can select it, and then press on H and enter, and then we select an enter point. So we select this point, for example. Very good. Then we press on escape, and then we select the automatically adjust the hatch scale. Alright, now we need to attach this busbar to this circuit breaker. So we can select it, and we can press on M and enter, and we pick it from this point, and then we can attach it to this point. Alright, After that, we need to add the earthing busbar of the distribution panel, and for that purpose we can express the earthing busbar by a line under this busbar here or under this three-phase busbar. So this three-phase busbar represents the three phases of the distribution panel, but we need another busbar, or we need another indication for the earthing busbar for this distribution panel. And for that purpose, we will draw another line. So we press on L and enter, and we can start from this point here, and we can go there until that point, and then we can draw another perpendicular line until this point. Very good. Now we press on escape. Then we need to change the color of the earthing busbar. So we need to distinguish between the main busbar and the earthing busbar. And for that purpose, we can give the earthing busbar or the earthing line a yellow color. So we can select it and select this one also. So let's select it. And then we can change its color to be the yellow one. Alright. Also, we need to connect this earthing busbar to the earthing sample that indicates that this is an earthing busbar. And for that purpose, we jump to the legend we have, or we jump to the distribution panel legend. And here we find this is the earthing sample. So we can select it, and we can press on CO and enter to copy it. Then we select it from this point, and then we go there until this point, but we need to deactivate the ortho mode. So we go to the ortho mode, we deactivate it, and then we select it at this position. Very good. Now we press on escape. Alright. So this is for the three-phase busbar and for the earthing busbar. Now we need to draw the lighting outgoings of this distribution panel. So this is the input of this distribution panel, and we need some outgoings of this distribution panel also. Hence, we can draw a line outgoing of this busbar, which represents the connection of one circuit for the lighting circuits. So we press on L and enter, and then we activate the ortho mode again. Then we can draw from this point, then until this point, and then we press on escape. Now we need to trim this part, so we press on TR and enter, and select those objects, and then press on enter and trim this part. Very good. Now we press on escape. After that, we need to connect this line to the single phase circuit breaker that will control the lighting loads of this circuit. And for that purpose, we have also the sample for the single phase circuit breaker. So we can select it and press on CO and enter, and we start from this point, and then we deactivate the ortho mode. After that, we go to this position. Here we insert it at this point. Very good. Now we press on escape. So this is a single pole circuit breaker that will be connected to this circuit, which controls some luminaires that are included in this circuit. After that, we need to draw the cable that will connect the power from this circuit breaker to the lighting loads. So we do the same thing. We press on L and enter. Then we start from this point until this point here, and then we press on escape. Very good. Now we need to express the type of the electrical loads that this breaker is going to feed. So this breaker will feed some luminaires or some lighting loads, and for that purpose we will draw a rectangle. So we press on R, E, and C, and we press on enter. Then we start from that point until this point here. Very good. Now we need to rotate this rectangle, so we select it and press on RO and enter, and we start from this point, and then we make the rotation angle to P45 degree, and then we press on enter. Alright, now we need to connect this rectangle to the end of this circuit, so we select it and press on M and enter. Then we start from this point and we add it at this position. Alright, so this rectangle will represent the circuit, or it will represent the type of the loads that this circuit breaker will feed. But at this circuit will not be just one circuit, so we will use it to refer to the number of circuits that will be connected to the first phase R. Hence, we can type the letter R under this circuit here. So we type a text by pressing on T and enter. Then we specify this area for the text, and then we type capital R, and also we can pull it, so we can select it, and then we can change its font, so we can select it and change its text to be Century Gothic. Here, that's it, and press on enter. Alright, now this is our letter. You can see it's very small, so we can select it, and we can change its scale by pressing on SC and enter and specify the space point. Then we can make its scale to be 200 and then press enter. Alright, also we can change its scale, or we can increase its size by selecting it, then press SC and enter and select this space point, and then we can increase its scale to P10 and press enter. Alright, now we can select it and we can move it to P down here. Now at that point we need to revise the number of circuits that were connected to the phase R and the lighting distribution panel, which we have designed its balancing design before. So for that purpose we jump back to the Excel sheet which we have designed. Here you can see this is our Excel sheet, and we can find easily that the phase R has 5 circuits connected to it. The first circuit is 150 volt ampere, the second one 150 volt ampere also, the third one 100, and the fourth one is 100, and finally the fifth one is 200 volt ampere. So those are the power values for the 5 circuits connected to the phase R. Now we jump back to our single line diagram to add them. Here we need to type another text, so we can select this one and press CO and enter, and we select this point and paste it here. Then we can select this one and change it, so we can change its text to P, 5 circuits. Then we press on escape and press yes. Then we need to decrease its scale a little bit, so we press on SC and enter and select the space point, and then we can make its scale to P 0.4 for example. Alright, now we select it and move it to add it inside this box. So when we press 5C here inside this box, this means that we have 5 circuits connected to this line. So this line is not only just one circuit, but it's 5 circuits, as here it's 5C or 5 circuits. Also we can add the multiplication samples, so we open it and make the multiplication samples, and then we press on escape and then yes. Then we can move it a little bit. Very good. So we have 5 circuits inside this line, or we have 5 circuits connected to the phase R. And then we need to type the power values connected to those circuits in the actual design of the phase R, or we need to know what are those circuits which will be connected to the phase R. Hence we can draw an arrow by pressing on L and enter. Then we start from this point until this point here, and then we go until this point. After that we press on escape, and then we can mirror this one, M, I, and enter, and select this point as the first point for the mirror, and select this second point, so this line will be the mirror line, and then we press on enter. Very good. So this is the arrow upper which we will type the power ranges of those 5 circuits that will be connected to the phase R. But at first let's select this arrow, and we can change its color to P, red one. Very good. Also we can move it from this point here, and we can add it at this position. Very good. Then to add the power values we need to type a text, so we select this text and press C, O, and enter, and then we select this one and we can add it at this position. Then we can change the text, so we press Ctrl A. Then we add the power values to P150, and then 150, and then 100, and then 100, and finally 200. And then we add a parentheses and another one at the beginning. Then we set its unit to P volt ampere, and then we press on escape and yes. So those are the power values. Here we can select them, and we can decrease its scale, so press on SC and enter and select this point, and let's make its scale to P 0.6 and press enter. Very good. Now we select it and center it at this position, And finally, under this arrow, we will type the number of circuits from C1 to C5. So we select this text and press C, O, and enter, and add it under this arrow. Then we press on escape, and then we select it and press Ctrl A, and then we type C1 to C5, and then we press on escape, and then yes. Then we can move it to P at this position. Very good. After that, we need to specify the circuit breaker rating, and we need to specify the cross-sectional area of this cable connected to each of those 5 circuits. And if you remember, as each of those circuits has a power value that is less than 1200 volt ampere, so its standard cable cross-sectional area will be 2 millimeters square. Hence, we can use 3 single core cables, and each of them is rated 2 millimeters square. So let's type another text by selecting this text, for example, and copy it, CO, and enter, and we can select the space point and paste it here, and then we can change the text. Here we press Ctrl A and make it to be 3 times 2 millimeter and square. Then we press on escape and yes, and then let's move it to the right a little bit. So this means that we have 5 circuits, and each of them, or each circuit of the 5 circuits, has 3 cables. One for the line, and another one for the neutral, and a third one for the earthing. And all of them is rated 2 millimeters square, or each of them has a cross-sectional area of 2 millimeters square. After that, we need to specify this single pole miniature circuit breaker rating. So for this miniature circuit breaker rating, if you remember also, as this line or this circuit has a power range that is less than 1200 volt ampere, so we will select the rating of this circuit breaker to be 10 ampere. And for that purpose, we select this text and then press CO and enter and add it at this position, and then press on escape, and then we can select this text and press Ctrl A and make it to P 10 ampere, and under it we make its type to P miniature circuit breaker, and then we close the text editor. Very good. Now we can center it also. Here we justify it at the center and then press on escape and yes. Now we can change its position also to P at this position. Alright. Also, we can change the color of all of the texts we have, so we can select this text and this one, and this one, and this one, and this text, and this one. Then we can make their color to be green ones. Very good. Now we need to repeat what we have did on this circuit or on those 5 circuits, but we need to repeat them for the phase S or the second phase. As we have 3 phases, phase R, phase S, and phase T, so we need to add the circuits that will be connected to the second phase, which is the phase S. And for that purpose, we can select those objects. Then we press on C, O, and enter. Then we select this point, and after that we go there until this point, and then we add them a third time at this point. Very good. Then we press on escape. And also we need to extend this busbar or this 3-phase busbar a little bit, so we can select it, and then we press on EX for extending it, and then we press on enter, and for that purpose we can select this 3-phase busbar and this earthing busbar, and we can copy them, press C, O, and enter, then we can select them from this point, and then we can paste them at this point. Very good. So we have extended our busbar we have. Then we can select the circuit and we can move it to the right a little bit. So we press on M and enter, and then we can add it at this position. Very good. Also we can move this second phase a little bit. So we press on M and enter and make it at this position. Alright, so those are the 3 phases we have, but we need to change the data for those two phases, the phase S and the phase T. Hence, for the miniature circuit breaker and for the cable cross-sectional area, there will be the same. But for the number of phases that will be connected to the phase T, so we can check them also from the Excel sheet. Here, as you see, the phase S has 4 circuits connected to it. They are 150, 300, 150, and 150. So we jump back to the AutoCAD, and then we change the number of circuits to be just 4 circuits, and then press on Close Text Editor. Then it will be phase S, and then press on Escape, and then Yes. And here we change the power ranges. The first one is 150, the second one is 300, the third one is 150, the fourth one is 150, and that's it. Then we delete this fifth one, and then press on Close Text Editor. Alright, then it will be from circuit 6 to circuit 9, so starts from circuit 6 till circuit 9, and then we press on Close Text Editor. And finally, for the third phase T, we will have the same thing. If we jump back to the Excel file, we will find that it has just the 3 circuits connected to it. So we make them to be 3 circuits, and then Close Text Editor, and then it's phase T, then press on Escape, and Yes. And their power ranges are 300, 100, and finally 100. So we made them to be 300 volt ampere, 100 volt ampere, and finally 100, and we delete those 2 circuits. We don't need them, and press on Escape, and Yes. And it will start here from 10 till 12, so it's circuit 10 till circuit 12 to have finally 12 circuits connected to this distribution panel or connected to this lighting distribution panel. Very good. Now we need to adjust this ingoing circuit breaker, so we select it, and then we press on M and enter, and we start from this point, and we adjust it at this point. Very good. Also, we need to type the name of this distribution panel, and we need to add its sample, and for that purpose, we go to the legend we have. So we have this distribution panel sample. We can copy it, press C-O and enter, and select it from this point, and add it at this position. Very good. Then for its name, here we can copy this text, press C-O and enter, and then add it at this position, and press on Escape. And for its name, it will be the first floor lighting distribution panel, as this lighting distribution panel lays on the first floor of the building. So we made its name to be F1 for the first floor, and then LDP for indicating that this is a lighting distribution panel. Then we press on Escape and Yes, and we can add this text at this position, and that's it. After that, for the 3-pole circuit breaker, we need to select its rated current. So its rated current is 16 ampere, and it's a 3-phase miniature circuit breaker. So we can copy this text here, press C-O and enter, and copy it and paste it at this position. Then we change the text here, or we change its rated current to P16 ampere, and then press on Close Text Editor. Alright. Also, for the cable that is connected to the circuit breaker, it's a 3-phase cable, and it will have a cross-sectional area of 6 millimeters square. So we can select this arrow and press on C-O and enter, and we can copy it from this point, and we need to paste it here. Then we need to change its scale by pressing on SC and enter, and select it from this point, and make its scale factor to P 0.5, and press enter. That's good. Also, we need to rotate it, or O and enter, and make its rotation angle to P 180 degree, and press on enter. That's good. Now we need to refer to this cable, so we select this arrow and press on M and enter, and start from this point and make it at this position. Very good. Here we need to type the data of this cable. Then we press on C-O and enter and select it. Then we add it at this position, and here we change it to P4 as we have 4 cables, 3 of them for the 3 phases R, S, and T, and the 4th one for the neutral. And each of them is rated 6 mm square. So this is the input cable for the distribution panel, and then we press on escape, and then yes. So that's about our distribution panel, and we can add it on a specific box. So we press on R, E, and C to draw a rectangle, and then press on enter, and we specify the box to P, this one. Very good. Also we can change its weight, so we can make its weight to P 0.25. But you can see the weight of the line hasn't been displayed, so to display the line width, we type the command LWD and select the second one, and then press on enter, and after that we can select the weight of the color to P, this one for example. Very good, so that's about this rectangle that include the lighting distribution panel we have, and that's about designing and drawing any distribution panel by the same way. So that's about this tutorial. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In this tutorial we will start talking about a new important topic in the field of the distribution system, which is the earthing system. So fasten your belt and let's get started. The aim of this tutorial is to know what is the earthing system, as we need to know the idea behind the earthing system. And then we will learn why we need to use the earthing system, or what is the importance of the earthing system. And finally, we will start on discussing the different components of the earthing system, as we need to understand each part of the earthing system and how can we use it. So let's go ahead. First of all, if we need to know what is the earthing system, we say that it's a protective system which connects all the exposed parts of the electrical devices with the ground. So for the earthing system, it's used primarily as a protection system which protects the electrical devices through some kinds of electrical faults. And this protection is done by connecting the exposed parts of the electrical equipment or the external parts of the electrical components to the ground. And we do so because in some cases there is a leakage current that passes through the equipment. So we need to discharge this leakage in the earthing system. Hence, this leakage on the external body of the equipment is absorbed by the earthing system. And this earthing system is designed to have a specific value of resistance that the earthing system mustn't exceed, or it mustn't go larger than this value, as it should be less than 1 ohm for the earthing system designed for the high voltage applications and the generating stations. While for the low voltage applications and the medium voltage application, this earthing resistance must be less than 5 ohms. So for the low voltage applications, this earthing resistance has a larger value than the high voltage applications, as here it can be up to 5 ohms, while in the high voltage applications it must be less than 1 ohm. Very good. Now you can ask, what is the use of the earthing system? Here we say that the earthing system is used in some protective purposes, and the first protective purpose is to protect human against electrical shocks. This is because in some cases there is a leakage current that reaches the surface of the electrical equipment, and the problem here is that if the human touches those exposed parts of the electrical equipment, he will be shocked as the current will pass through his body. So we use this earthing system at that case by connecting the exposed parts of the device to the ground directly for the ground to absorb any leakage current, as the leakage current at that case will find an easier way to go through, which is the earthing way, and no current will pass through the human body. And this is because the leakage current at that case will find 2 parallel paths to go through. The first one is the human body, which has a larger resistance of 1000 ohm, and the second one is the earthing path, which has a smaller resistance of 2 ohms only. So the total current will pass through the earthing path due to its smaller resistance, and no current will pass through the human body due to its larger resistance. And by that way, we are protecting people against the earth leakage when connecting the machine putty to the earth. Alright. Also, the second reason for which we are designing the earthing system is to protect the electrical devices themselves against the leakage current, as if this leakage current goes through the external putty of the equipment itself may be damaged. So we protect the equipment and we are improving its lifetime by connecting it to the earthing system to absorb any leakage current, as the total leakage current will pass through the earth due to its very smaller resistance. So as we said, the earthing is having a very smaller resistance, hence the total current will pass through it. Very good. Now, after knowing what's the earthing system and why we are using it, we need to know what are the different components of the earthing system. Or we need to know what are the main parts that the earthing system is having. Here we find the first part of the earthing system to be the protective earthing conductor, and this protective earthing conductor is the conductor that connects the equipment exposed parts to the main earthing conductor, as each device and the electrical devices must be connected to the earthing system through its exposed parts. So we say that this protective earthing conductor is the first main element in the earthing system. For example, suppose we are having 3 devices that we need to connect to the earthing system. So we use 3 earthing conductors, one for each device, and it will be connected to the main earthing conductor. And finally, this main earthing conductor is connected to the main electrode. But now for the protective earthing conductor, we select its cross-sectional area to have the same cross-sectional area of the main conductor in case of the conductor's cross-sectional area is less than or equal 60 millimeters square. So at that case, the phase R equals the phase S equals the phase T, and they are equal the neutral also, and they are equal the protective earthing cross-sectional area. While in case of the main cable cross-sectional area is larger than 60 millimeters square, the earthing conductor at that case will equal half of the main conductor cross-sectional area. Hence, the phase R equals the phase S equals the phase T, and they are double of the main conductor cross-sectional area. Alright, but the important note here is that the protective earthing conductor can be a separate cable which is separated from the main conductor cable, like that case here. You can see the earthing cable is a separate core which is connected to the exposed parts of the equipment directly. And it may be a core that is included inside the main supplying cable. So it will be connected to the exposed parts of the equipment also. Alright, so that's for the protective earthing core. Now the second component we have is the earthing conductor, which is the main conductor that connects the protective earthing cable to the main electrode of the earthing. So it's this cable that is connected directly to the main electrode of the earthing system. But you can ask now, how can we detect this conductor cross-sectional area? Here we say that this conductor cross-sectional area equals the short circuit current times the square root of the time that this short circuit current will pass through over a factor that is called the K factor. And to detect this short circuit current, it equals the maximum short circuit current that can occur in the distribution network. And we learned it before how to calculate this short circuit current through the manual calculations or through the ETAP calculations. So once we detect the maximum short circuit current, we can calculate the cross-sectional area of the earthing conductor. After that, for the time, it's the time that this short circuit current will last to go through the circuit before tripping the circuit, and it's set to P 0.1 second for the low voltage systems. So we can set it to P 0.1 second. And finally, for the K factor, it's the current density, or it's the density of the short circuit current that will pass through the circuit, and its unit is ampere per millimeter square. And to select this current density, we can select it from some standard tables, as we select it according to the maximum temperature of the short circuit current that can pass through the circuit. as here we detect the maximum temperature from this table. And also we select it according to the material that this earthing cable is made from, and it may be a copper or aluminum or steel conductor. So according to the maximum temperature and the conductor material, we select the current density of the short circuit current. And here to select the maximum temperature at the short circuit current, we can set it with a middle value that may be, for example, 350 degrees Celsius, and we can select the cable material to be copper. So at that case, the intersection between this column and this row will give us a current density of 201 ampere per millimeter square. Alright, so that's for detecting the second component, cross-sectional area. And now for the third component we have in the earthing system, it's the main electrode. And this main electrode is usually an electrode which is digged inside the ground, and it's connected to the main cable to absorb the electric current and discharge it inside the ground directly. And the very important parameter which is related to this electrode is the resistance of the earthing system, or the final resistance that the earthing system is having. And as we said, our final aim is to design an earthing system which has a very smaller earthing resistance, which is smaller than 5 ohms for the low voltage applications. So to detect the resistance of the earthing, it equals rho over 2 pi times L times ln 8 times L over D minus 1. So let's anchor this equation step by step to know how to detect its different parameters. Here rho is the soil resistivity and its unit is ohm per meter, and this soil resistivity is the resistivity of the soil that we designed the earthing system for which, as each type of soil has a specific value of resistivity that is different from the other type of soils, and we can detect the soil resistivity from this table here. You can see for the clay soil, for example, its resistivity is 40 ohm per meter, which is a very smaller value. And for the sand resistivity, its resistivity equal 2000 ohm per meter, and so on. So according to the soil we are working on, we can detect its resistivity from this table. And then the second parameter is L, which is the length of each single electrode in meter. And we have a standard table for detecting the electrode length. And then for D, it's the single electrode diameter, and it has some standard diameter values which we can select from. Alright, now the important question is that if we calculated the earthing resistance from this equation and we find it to be larger than 5 ohms, how can we modify this design to reduce the value of the total earthing resistance? Here we can perform this by adding 2 additional electrodes in parallel. As from the basic electrical circuit principles, we find if a single electrode resistance equals, for example, 10 ohms, the double electrodes which are connected in parallel will have a smaller resistance than 10 ohms. So we have finally a total resistance less than 10 ohms in case of the parallel electrodes or in case of having some electrodes connected in parallel. And to detect the total resistance of the earthing system in case of having an n number of electrodes, we can detect it from this equation, as the total resistance of the total earthing system will equal the single electrode resistance times 1 plus lambda times A over N. And here R sub N is the total resistance of the system, and R is the resistance of the single electrode, and then lambda is a factor that we detect from this standard table, and it depends on the number of electrodes we are using. As in case of having 2 electrode system, we set lambda to P1, while if we are using 3 electrodes, for example, we set lambda to P1.66 and so on. And after that, for the parameter A, we detect its value from another equation, which is this equation here, as the parameter A equals rho over 2 pi times R times S, where rho is the soil resistivity, and we detect it from the same table which we explained before, and R is the single electrode resistance as we said, and then S as the distance between each two adjacent electrodes. For example, if we are having 3 electrodes which performs the earthing system, we measure the distance between each two electrodes to PS. And finally, N as the number of electrodes we are using, which may be 2 electrodes, 3 electrodes, or 4 electrodes, for example. More than great. So that's about this tutorial at which we took an idea about the earthing system and we started talking about the different components of the earthing system, and on the next tutorial we will continue talking about the earthing system different components. That's it right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In this tutorial, we will continue talking about our new important topic, which is the earthing system. So fasten your belt and let's get started. The aim of this tutorial is to continue discussing the different components of the earthing system, as we started talking about those components on the previous tutorial, and we need to end them now. And then we will illustrate how to measure the earthing system resistance. So we will illustrate the different steps of measuring the earthing system resistance. So let's go ahead. Now we need to start with the fourth element in the earthing system parts, which is the earthing hole. And this earthing hole is the hole that the electrode is digged inside. And for this earthing hole, it has some properties. And the first property of the earthing hole is the hole depth. So we need to know what is the depth of the hole that is used in the grounding system. And here we say that the grounding hole depth depends on the soil type itself. As for the agricultural soil, its depth ranges from 1 till 5 meters. So if the soil we are working on is an agricultural soil, we dig a hole with a depth that ranges from 1 till 5 meters. While if the soil is a sandy soil, we dig a hole with a depth that ranges from 3 till 6 meters. So this is the first property of the grounding hole. Now the grounding hole's second property is that we add a specific type of coal to the hole, and the reason of adding this coal is to increase the conductivity of the grounding system and decreases its resistivity, as the coal increases the soil properties of having a larger conductivity, and also it decreases the chemical reactions between the soil and the electrode. This is because when the electrode is added inside the soil, the chemical reactions between the electrode and the soil affects the electrode badly, and it causes the electrode corrosion. So we avoid this corrosion and we decrease the soil resistivity by adding this coal to the soil. Very good. Also, the third component we add to the soil is the salt, and this salt is added to increase the conductivity of the soil, as our final aim is to have a smaller resistance of the earthing system. So we add the salt as it decreases the soil resistivity and it increases the soil conductivity. Alright, now we need to know how can we measure the grounding resistance or the earthing resistance. So we need to know how the earthing resistance is measured. And here we find that we have a device that is called the earthing measure, which is used to measure the earthing resistance. And for the measuring purposes, we dig 2 other smaller electrodes in addition to the main earthing electrode, and we dig them on a certain distance, which makes the distance between the main electrode and the first electrode to range from 5 till 10 meters. And the distance between the first electrode and the second electrode to be the same distance that ranges from 5 till 10 meters. And after that we find the measure device to have 3 terminals, and those 3 terminals are connected to the 3 electrodes. As the main electrode is connected to the earthing terminal of the measure device, and the first electrode is connected to the potential terminal of the measure device, and finally the final electrode is connected to the current terminal of the measure device. And as a final result, we find the measure device to measure the earthing system resistance. And as we said before, this earthing system resistance is needed to be less than 5 ohms for the low voltage and the medium voltage systems, and it's needed to be less than 1 ohms for the high voltage system. But the question now is that, what if we measured the soil resistance and we found it to be larger than 5 ohms, for example? Here we need to know how can we improve the design of the earthing system. At that case, there are some parameters that we can modify or adjust to decrease the earthing system resistance. And the first parameter of them is the coal, as we can add much more coal to the earthing hole to increase its conductivity or to decrease its resistivity. And also the second parameter is the salt, as if the hole resistance is larger than the required value, we can increase the amount of salt inside the hole to increase its conductivity or to decrease the total resistance of the earthing system. This is, as we said before, because the salt and the coal are used to improve the property of the conductivity for the soil. But on the other hand, if we try to modify those two parameters and we found that the earthing system resistance is a larger one, or it is still to have a larger value, at that case we can increase the number of electrodes used in the earthing system. So if we are using one electrode, we can add an extra electrode or 2 other electrodes. So those are the ways by which we can improve the earthing system or we can decrease its resistivity. More than great. So that's about this tutorial, and on the next tutorial we will discuss the different types of the earthing system. Hope that's it right now. Thank you for watching and see you next tutorial. Hello and welcome everyone. I'm very happy that we're all together again. In this tutorial we will continue talking about our topic, the earthing system. So fasten your belt and let's get started. The aim of this tutorial is to discuss the different types of the earthing system, as the earthing system has some different types, so we need to know what are those types. So let's go ahead. Now the first main type of the earthing system is called the source earthing. And from its name we find the supplying source to be a part that is earthed. So we are focusing on the source now to be the earthed part. But as we know in the low voltage system, the source is the distribution transformer itself. So if this is the distribution transformer, and this is its medium voltage side or its medium voltage windings, which is delta connected, and this is the low voltage side which is star connected, and at the solid earth the neutral point of the low voltage side is directly connected to the earth, or it's called the solid earth. But at that case the earthing resistance must be a very smaller one, which is less than 2 ohms. So if we design an earthing system at which the neutral point of the transformer is connected directly to the ground, which has a resistance less than 2 ohms, this type of earthing at that case is called the solid earth, as the earth has a lower resistance. Alright, now the second type of the source earthing is called the resistance earth, and this resistance earth has the same idea of the solid earth, except that the earth at that case is having a larger resistance, which is larger than 2 ohms. So the neutral point of the low voltage side is connected to the earth directly, but the only difference here is that the earthing resistance has a larger resistance that is larger than 2 ohms. Very good. Also, the final type of the solid earth we have is called the isolating earth, and at that type the neutral is not earthed, so it's not connected to the earthing system, but the exposed parts of the transformer is the part that is earthed. So we find here that the outside parts or the external parts, they are the parts that are connected to the earthing electrode, and for that reason this type of earthing has a high impedance, or it's a highly impedance system, because the external parts represents a high impedance. And from here comes the name of the isolating earth, as the earth is isolated from the neutral point. And this is the actual shape of the isolating earth for the dry transformer, as at that case the external or the exposed parts of the transformer are earthed, as they are connected to the earthing system through the earthing cable, as you see. Very good. Now the second type of earthing we have is called the load earthing, and at that case the part that we are focusing on now is the load that is connected to the transformer. So we are including now the load to the earthing system. And we have some types of the load earthing, as the first type of the load earthing is called the TT system, and this TT earthing system has some properties. And the first property of the TT earthing system is that the electrical load exposed parts are connected to the ground or to the earth. Hence, at that case, the electrical load neutral point is isolated from the ground, while the exposed parts or the external parts of the electrical load are the parts that are connected to the earthing system. And also its second property is that the transformer neutral point is earthed directly, or it's connected directly to the ground. So the transformer earthing here is opposite to the load earthing, as the transformer earthing is connected to the neutral point, while the load earthing is isolated from the neutral point, but it's connected to the exposed parts of the electrical load. And also the third property of the TT system is that the source earthing is totally isolated from the load earthing, and this means that there is no link or no connection between the source earthing and the load earthing, or they are totally isolated from each other. So we can summarize the TT earthing system in that the source neutral point is earthed directly to the ground, while the load exposed parts are earthed to the ground, and the load earthing is totally isolated from the source earthing. Alright. Now the second type of the load earthing is called the IT earthing, and at that type of earthing the source exposed parts are earthed to the ground, so the neutral point is isolated from the ground. And the same thing for the load, as the load neutral point is isolated from the earthing system, while the exposed parts or the external parts are the parts that are connected to the ground. And at the same time, the load earthing is totally isolated from the source earthing, so there is no connection between the source earthing and the load earthing. And also we can summarize those steps in that the source exposed parts are earthed, and the load exposed parts are earthed, and at the same time the load earthing is isolated from the source earthing, or there is no connection between them. Very good. Also, the third type of the load earthing is called the TNC system, and at the TNC earthing system, the neutral point of the source is earthed directly to the ground, and the load neutral point is earthed directly to the ground also. And at the same time, the load earthing is connected directly to the source earthing through a cable. So there is a connection between the source earthing and the load earthing, or the source earthing is not isolated from the load earthing. And by the same way, we can summarize the TNC earthing system in that the source neutral point is earthed directly to the earth, and the load neutral point is connected directly to the earth also, and also the source earthing is connected to the load earthing through a cable. And at that case, we find the neutral cable to be the same cable of the earthing cable. So we use the same cable as a neutral cable or as an earthing cable. Alright. Now the final type of the earthing system we have is called the TNS earthing system. And this type of earthing is the same as the TNC earthing system, except that the earthing cable here is a separate cable from the neutral cable. So we are having two cables now. One cable for the neutral, which is connecting the source neutral point to the load neutral point, and another cable for the earthing, which is connecting the source earthing to the load earthing. Hence, at that case, we find the source neutral point to be earthed directly and the load neutral point to be earthed directly. But there is a cable for the earthing which is separated from the neutral cable, which is connecting the source neutral point to the load neutral point. More than great. So that's about this tutorial at which we finished talking about the different types of the earthing system. Hope that's clear right now. Thank you for watching and see you next tutorial.